Just a moment. Okay, good evening, ladies and gentlemen. Good morning to those joining us from the US and good afternoon to those joining from Germany. Welcome to the second session of A to Z Physics Education by the Out of Syllabus Society, or TOS for short. We aim to provide a deeper understanding of various fields and vocation through the eyes of established professionals and educators alike, and introduce them to our students so they can make well-informed decisions in the future. To get fresh updates on our endeavors, we highly suggest you to like our Facebook, Instagram page and subscribe to our YouTube channel. That being said, we have an upcoming and final session tomorrow with Padma Shri Verma ji, and the man who taught India physics and influenced how we understood physics as a subject. Before we move on, very happy Engineers Day to our audience. What an occasion for an engineer such as myself to address the understanding of physics. Now, to maintain an effective discussion, I would like to introduce our viewers with the structure of our podcast for today. We have an important announcement today regarding a free mentorship initiative, so please stick around until the end. The podcast will have three major sections. Section 1, which will be a 40 to 45 minutes uninterrupted discussion between the guest and myself. During this time, I sincerely urge all the parents, teachers, and the students in the audience to please use the chat to fill in their questions, thoughts, comments, etc. To give an equal opportunity to all, we will address them from chat in section 2. Section 2 will be handled by Namrata, who will address all the questions in the chat only. This will last for 15 to 20 minutes, depending on the number of questions that we have. And section 3 will be a free running discussion for about 40 to 45 minutes, depending on the number of questions again. And it will be more like a networking session between the speaker and the audience, where long questions, comments can be addressed effectively. Interested audiences can unmute themselves during that time, and video access will be definitely provided for effective discussion. So please stick around until then. It will be interesting, I promise you on that. So a little bit about our guest today. Yesterday we had as a quick recap, yesterday we had a great discussion with an established entrepreneur and an aeronautical engineer, Mr. Vaibhav Varun, on the topic of understanding the bare concept of physics and the underlying math. The video is now available on our YouTube channel, so do check it out. Today we hope to introduce our audience to a student much like you, who has been able to break the mold and engage himself with the top mind of the previous and the current century. Here is Mr. Utkarsh Bajaj. He's currently a junior research affiliate at Wolfram Physics Project and has just completed his 12th successfully. And now he's going to pursue his passion in Canada in the field of math behind physics. Meanwhile, Utkarsh has also written a book on general relativity, and there is an upcoming sequel to that as well. So stay tuned. The title is called General Relativity, Curvature and Geodesics. And a new edition is available and will be given as a signed copy to the most interesting and engaging question in this podcast. So please leave us your fantastic questions and your email details so we can contact you further specifically. It's also available for those who are interested in the soft copy version of it or Kindle version of it on Amazon. So do check it out as well. Utkarsh is also particularly interested in starting a mentorship or a project initiative up to 3 interested students under his wing. We will discuss more about that in the final section of today's podcast. So stay tuned and watch until the end. We'll surely discuss about this. For those who don't know about the Wolfram Foundation, a short introduction is here. It's a leading research group trying to understand and replicate the fundamental theories of our universe through a computational process. Utkarsh here is directly under the mentorship of Dr. Stephen Wolfram himself. And Dr. Stephen Wolfram, as the name suggests, is the person spearheading the whole Wolfram Physics project. And if anyone is interested to check it out, they can find out at wolframphysics.org. Any more resources on this topic or science education materials should you request, will already be provided to you via emails, and also will be in the YouTube description once this video goes live. So before moving any further, let's have a few words with our speaker today. So hi Utkarsh, how are you? Pleasure
I'm
to have
good.
you.
I'm good. Thank you. Thank you for having me. I think this is a really great initiative, and we can make a lot of change with this.
That's really good to know. That's a good to know to come from a student such as yourself. Um, how did you get interested in physics, to be honest? That's my first question.
Right. So when I was in 5th or 6th grade, I was not interested in physics. I was interested in cricket. So I used to spend all of my time playing cricket for school. I used to go to an academy, and I wasn't a good student. Like, I did not get good grades particularly. I still remember in my nursery, in my nursery class, in my report card, I had a D. Like, which kid in nursery grade gets a D? I was the one. So the thing is, it was kind of like a spark for me, because when I was in like 7th grade or 8th grade, I don't really remember, 7th grade, I watched a documentary on YouTube because I was a heavy procrastinator on YouTube, and I clicked on this documentary by Brian Greene. It's called Fabric of the Cosmos. Yeah, it's a really like fancy name, and it is, and the way it's presented to us as like a general audience, the video is so good in explaining like high level physics concepts in a really easy to understand way. And it's done, and Brian Greene made the video, and he's a physicist at Columbia University, and he's known for delivering physics in an understandable way to curious students. So I watched that video and my mind was blown, because he told me such interesting stuff about physics that I had never learned, like even in school or like anywhere else. So that moment was kind of a spark for me, and from there, instead of watching TV, I started watching documentaries on YouTube. And even though they were non-mathematical, they gave a really good impression about what physics is and where it is moving in this century. And so that was this, the main spark for me. And then what really happened is, when I was in 8th or 9th grade, in 8th grade, I went to Switzerland for a family vacation. And I was really fixated on going to CERN. So CERN is the world's largest particle physics laboratory. It has the world's largest particle accelerator called the Large Hadron Collider, and it's a ring of particles. They move at 99.99% of the speed of light in a tunnel that is 27 kilo that is like underground, and it has a circumference of 27 kilometers. And the particles move around and they collide, and when they collide, they produce new particles. And when I went over there, I learned all this stuff, and even though I understood like 1% of it, I was so fascinated about the work that certain scientists were doing over there. They had like, when I went there, the facility was so modern. Like, they had these big computer screens. Like, if you've seen Iron Man's workshop, you know what I'm talking about. So, but Iron Man is a movie. This was in real life, and I was like really fascinated. It was like a science fiction movie itself. And from there on, and actually, fun fact, if you go to CERN, if you go to the shop, there's a t-shirt and like a bunch of mugs and stuff. On that, you've some an equation is written. That equation is called the Lagrangian for the standard model. So the Lagrangian
Sounds
for the
fancy.
standard model, okay, so a Lagrangian is something that can help you study the behavior of a system. So it can be a particle moving, it can be two particles moving, it can be whatever. And the Lagrangian for the standard model basically has everything inside it. It has particles, it has gravity, it has all of the four fundamental forces of the universe. And it's called the equation of everything. It correctly predicts to 100% every experiment on Earth. And that equation, if you write it in full form, will be like 2 pages long. They had a souvenir with like just they had shortened the equation by something known as a Hermitian conjugate or whatever, and then they wrote it on that, the t-shirt. So I was like, how can an equation exist which explains everything? And from there on, I became interested in physics.
That's quite a progress. क्योंकि as a student, I mean, when जब मैं physics सीख रहा था back in like almost a decade back, there was a time when I did not want to actually learn physics for any sake. भले ही वो आयरन मैन आके सिखाए या कोई भी आके सिखाए, मुझे सीखने का इंटरेस्ट नहीं था. बट that's quite a jump that you have done at a very young age, from a person who just visited CERN to a person who is actually working on theoretical physics, that too with Wolfram. So yeah, can I consider this to be a point like this? आपका जो ट्रिप था, एक ट्रिप जाना, ऐसे एक कोई भी एक म्यूजियम या फिर कोई भी एक साइंटिफिक एरिया, ऐसे रिसर्च एरिया, जैसे अपना हो गया BARC. Our BARC could also be considered as one of the world's top research centers as well, right? So students, अगर they expose themselves, अगर उनको भी जाके देखने को मिलेगा ये, do you think this can actually spark as a good interest towards physics? Can it spark an interest towards physics?
Right, that's a good question. Because क्या होता है कि if you go to some facility and वहाँ पे बहुत interesting चीजें हो रही हैं. So the thing about these facilities is that like BRC and CERN and other research institutes, IISc, IIT, even like our IIT universities also have very good laboratories. The thing is, वहाँ पे जो research होती है, it's really like groundbreaking. It's every lab in the world is doing research that is currently happening in the world. Obviously, that's a obvious statement. But the thing is, in class में हम जो सीखते हैं, that's not of that level, like not even near that level, because in class we are taught 1600s के चीजें, like Newtonian mechanics, F is equal to ma, gravity is a force that pulls something down, but we don't know what gravity is. Gravity एक force है, but force तो बस एक नाम है डिक्शनरी में जो हमने दिया है. It doesn't really explain what actually is gravity. So if you go to some place like this, you can definitely get fascinated, because first of all, it will expose you to a lot of things that you've never ever seen, which was my case. And second, it's just like one of those science fiction things जो होता है, and you're like, ये क्या हो गया, मैंने अभी क्या देखा, I don't even get what I'm seeing right now. And that is like basic human curiosity says that I want to explore this, because it's just like a science fiction movie. But the main part, the key thing is that it's not necessary that you will get excited when you go there. You have to have some previous कि मुझे यहाँ जाना है, because there are people who go over there and then they're like, I don't understand anything, so let's just come back. You try to make an effort to what you're saying. You understand the magnitude of the place that you are at, like understand what that place stands for, and then you'll actually get to know कि अच्छा, this is really exciting, and then you can do something.
Okay, that's quite interesting. But पहला क्वेश्चन तो ये माइंड में आएगा ना कि हम क्यों फिजिक्स पढ़े, फिजिक्स पढ़ने का रीजन क्या है, व्हाई शुड वन स्टडी फिजिक्स? आपका स्टूडेंट से पर्सपेक्टिव क्या था इसके बारे में?
Right. So this question is really important. Why? It's the motivation for every subject. अगर तुम मैथ पढ़ रहे हो, तुम्हें पता होना चाहिए क्यों पढ़ रहे हैं. But I think that's something that is missing in schools today, and many of the textbooks, in fact. When you learn something, when you learn F is equal to ma, we don't learn कि ये क्यों सिखा रहे हैं. We are just told कि न्यूटन एक बंदा था जिसके बड़े बाल थे, he invented this formula, वो पेड़ के नीचे बैठा था, एप्पल सर पे गिर गया, that's it. But the story is more than that. Why did Newton think of that in the first place? Why should one study physics? And that's a very good question. And the answer to that is, physics is basically the output of human thinking to explain the world. And to understand that, imagine there's some like alien civilization. अगर एक alien civilization है जहाँ पे कोई और intelligence है, उनकी physics क्या होगी? It will be similar to ours. Physics is ऐसी चीज है that will be part of every intelligence, because that intelligence is trying to figure out stuff about the universe. And that's why people say कि mathematics invented or is it discovered? Because mathematics is also one of those things that comes from our mind. So imagine that you're the first person on earth. मान लो तुम पहले इंसान हो जो धरती पे टपके हो, and then you're asking, ये क्या हो रहा है, right? You don't know what's going on. And then you see two apples on the ground, and you're like, you pick them up and you're like, मेरे हाथ पे दोनों का same, they feel the same to me. Then you say, okay, this apple is 5 and this apple is also 5 because they're the same. And that's how the notion of numbers came in, to compare two things. If one is 10 and one is 5, then humans can think, okay, this is exactly 2 times the 5 thing. The 5 can represent anything. It can represent the amount of taste like something has. So if apple has a taste of 5, a chocolate can have a taste of 10, something like that. So that's why numbers were invented. And then once this notion of math came in, there was this notion of mathematical modeling. तो mathematical modeling होता है, अगर तुम एक चीज देखते हो, तुम उसे numbers के through कैसे explain करते हो. You find patterns. Physics, the reason why we study physics is because humans want to see a pattern in everything. They
Physics
don't.
मतलब pattern देखने का एक तरीका होता है फिर.
Exactly, precisely.
Okay.
Because imagine you live in a world where there's no pattern to anything. If you for example, अगर मैं यहाँ से 5 मीटर दूर जाऊँ and I drop a ball, right, वो नीचे गिरती है. But now I go over here and drop a ball, it can't fly off, right? There is a pattern to everything. And therefore there is some rule to something, right? There is some एक rule है कि when I drop a ball, it should fall like that. There's a rule that if I throw the ball at some angle, it should go over there. So projectile motion या जो भी equations of motion है, they're just pattern identification things. So that's the only thing that is happening over there. We do some experiment, हमें pattern नजर आता है, and then we find a model to fit that pattern. And
pattern
over the
मतलब
years,
similarity, right? If I'm understanding it right. Okay.
Yeah, exactly. So there are many ways to see a similarity. एक है जो हमें स्कूल में सिखाते हैं graphs. So for example, let's give a different example than just dropping balls on the floor. Let's see what example I can give. Okay, let's see. There's an example of let's see a non-physics example to just show what a pattern is. When you buy a house, right? The house can be big or small. Bigger houses will be more expensive, right? So, and it's obvious that they will be more expensive. So then you plot a graph, right? X-axis पे house size, y-axis पे house price. As you increase the house size, you see that okay, house price बढ़ रहा है. And then you can just plot a graph. You can just plot points, एक line of best fit बनाओ, whatever. And that's like a pattern. So physics is now, instead of the house prices, house whatever thing, you replace that with actual physical experiments that you do. कि इस chemical को इसमें मिलाया. Even chemistry is all about patterns. Even biology is all about patterns. You test some medicine on a person, then you see whether it works or not. That's why it takes a lot of time for vaccines to get approved, because they have to see what pattern is that vaccine showing. Is that successful against this variant, that variant? So there are something that we can't predict a priori. That means पहले, without even knowing anything, we can't predict something. So we need that pattern, and उसके बाद ही हम predict करते हैं.
This is interesting. This is really interesting. We'll have to go. इसको थोड़ा section 3 में we'll go deeper.
Yeah, exactly. There's a lot to say.
We'll go a lot in this. Not a problem. My next question in mind would be this: कि as far as I have known you, मतलब in previous discussions and all, आप एक business family से आ रहे हो. आपका family background is more towards business, right? If I'm not wrong.
Yes.
आप एक थियोरेटिकल रिसर्च में जाने का जो एक बोलते ना एक एक्यूमेन, एक आपका इंटरेस्ट इस पॉइंट पे ये कौन से डायरेक्शन से आया था? आपने कैसे एक्सप्लोर किया था पहले ये कि मुझे बिजनेस में नहीं, मुझे थियोरेटिकल रिसर्च में जाना है, मुझे थियोरेटिकल फिजिक्स पढ़ना है, आई वांट टू अंडरस्टैंड द फंडामेंटल ऑफ द यूनिवर्स. ये इंटरेस्ट आपको कहाँ से और आपने कैसे ये प्रोसीड किया? कैसे रिसोर्सेस आपने पकड़े, कैसे आपने वो पोजीशन में अपने आप को भेजा?
इंटरेस्टिंग. तो द थिंग इज कि मैं बहुत लकी था. सो एंड मुझे अपने आप से कभी ये पूछना नहीं पड़ा कि मुझे बिजनेस में जाना है या इसमें जाना है. मैंने कभी डिसीजन ही नहीं लिया आज तक कि मुझे किधर जाना है. इट वाज when I did physics, I just did physics because I was interested in it, nothing else. And the reason for that is my family was really supportive. Like they didn't have any problem if I was doing math or whatever. And the thing is that when like even if I was in 12th grade or when I was in like 9th, 10th, 11th, 12th, whatever, they did not ask me what did I want to become, why don't you pick a stream and do this now. And there's a reason the world is moving towards this liberal arts education. So in the US, there's something known as a liberal arts college. The word liberal means that you're free to do anything you want, anything you want. So वहाँ पे क्या होता है, for the first 2 years you explore your interest, उसके बाद you choose something. According to me, for the first 20 years or so of your life, given the education system right now, it's meaningless to choose something unless there are financial problems or something else. If you just want to explore something for the sake of it, like interest के लिए, सोचो ही मत कि what do you want to become, because the world is changing so much. You can't even predict that if you do biology right now, you won't become a doctor. You can become something else. You can study the intersection between biology and, let's say, I don't know, like physics or something, right? Computer science, maths. There are so many connections between different subjects. I think people need to understand कि ये जो isolation हम करते हैं subjects का, कि मैं ये physics पढ़ूंगा, मैं ये पढ़ूंगा, मैं वो पढ़ूंगा, वो humans ने बनाया है so that पढ़ाई आसान हो. स्कूल में इसलिए करते हैं because we can keep our mind separate. Okay, मैं physics पढ़ूंगा, class खत्म, अब मैं biology पढ़ूंगा. If everything was in one curriculum, it would be very confusing. But the thing is, you have to realize these things are connected to each other in ways that we don't even know right now. So choosing something firsthand is not good because it limits what you can do in your life. And second, as I said, my family was really supportive. They didn't have any problem in me doing theoretical physics, or they just wanted me to like pursue my interest. And yeah, I think whatever I did, I started buying books and I just started reading and started watching videos, and that's how like anyone learns. So
I mean, yeah,
yeah.
in India there has been a lot of case. India में से कई सारे cases थे जो self खुद पढ़ के लोगों ने IAS clear किया है, और काफी सारे ऐसे examples देखने को मिलता है इंडिया में. Maybe that's another thing, that people who are not so lucky in that direction where their economic conditions, उनकी economy, घर की economy is not exactly very helpful उनके आगे वाले dreams को fulfill करने के लिए, maybe they can go in that direction of एक self learning initiative में. Do you have any tips or suggestions in that sense for them?
Yeah, I think yes, we do have to acknowledge that there are people from like in India. So, and yeah, I think this is a good question, and it certainly requires a lot of thinking. But from what I think, कि जितना मैंने इसके बारे में सोचा है, if someone, if your family household is not like let's say, giving you the permission or is not willing to accept that you want to do something, and it's not their mistake, it's not your mistake. So find common ground. What you can do is, nowadays everyone has mobile phones. You have a mobile phone, and literally knowledge is being distributed for free. Abhinav, you said this to me in our last meeting, and it is very true. Knowledge is being distributed for free. You can go to Google, you can type anything you want. In fact, I have a demo that I will show later in this meeting. मैं बाद में दिखाऊंगा कि कैसे Google को देख के आप इतनी सारी चीजें सीख सकते हो. And the thing is, you have, अपने पेरेंट्स के साथ या किसी और के साथ रीजन करो कि why this subject might be good. Search what are the applications of computer science in the future, and computer science is like the future. So just जो भी है, tell them to your parents, try to educate them. And if that doesn't work, you have like knowledge at your fingertips. Literally type something with your fingertips and get that information. So learn using your phone, buy a cheap laptop, or and most importantly, there are many libraries. Like there's a library in Chandni Chowk, there's a library everywhere. Go there, buy some books, and books aren't even that expensive. Start reading, because one book, like for example, this book has so much information inside it. Like, I think it will probably take me 3 years to finish this. A book contains that much information. You can either skim it or you can like really read this information. And once you finish this book, you feel really, really good and you learn a lot of stuff. So kitabi kharido, don't hesitate to get knowledge. However, like jitna bhi it, whatever it costs, buy things. And abhi knowledge is free, so you don't even need to buy anything. So yeah, just follow your interest, and self-learning is really important. That's what I wanted to say.
We'll definitely come to that resources वाला thing. We, जैसे मैंने पहले बताया कि we सारे resources आपको जो भी सीखने का वगैरह links वगैरह रहेगा, that will be provided later in the podcast, will be also provided via email and will be in the YouTube description if you check it out. So not a problem. I mean, ज्ञान तो हर तरफ से बट रहा है, like Rancho once said. So not a problem with
Last
that.
bed, right.
That's really good thing because this यही मेरे को क्वेश्चन ये पहले आया था कि आपने एक बुक लिखा है, करेक्ट? आपने एक आंसर आपने खुद फाइंड आउट किया कि ओके, आई वांट टू वर्क ऑन ग्रेविटी, आई वांट टू वर्क ऑन ग्रेविटेशनल थियरी, आई वांट टू वर्क ऑन जनरल रिलेटिविटी. ये चीजें आपने खुद आंसर्स फाइंड आउट करें आपके क्वेश्चंस के लिए. सो यू आर काइंड ऑफ लाइक ऑन द सेल्फ मेड डायरेक्शन. तो ये आपने किस तरीके से किया था? आपने ये नेटवर्क कैसे किया था लोगों के साथ पता करने के लिए, चलो मुझे ये आंसर चाहिए तो मैं इनके पास जाऊंगा, इनसे आंसर मैं पता करूंगा, फिर यहाँ पे यहाँ जाऊंगा, आंसर पता करूंगा. ये एक बहुत बड़ा स्किल होता है जो आजकल के स्टूडेंट्स में बहुत इंपॉर्टेंटली बताना पड़ता है कि करो. ये एक इम्पोर्टेंट चीज होती है. ये आपने कैसे किया था? और आपके पास जो डेमो है वो आप भी दिखा सकते हैं वैसे. That will be a good idea.
Acha. I can show the demo when we talk about the Wolfram thing. But right now this question is a bit different. So I think whatever effort, जो भी मैंने efforts करे थे लोगों को contact करने के, I didn't have to think that much to do that. It just came to me, and there's a reason for that. I think मेरे हिसाब से, if you have a passion or interest for something, then your mind will automatically tell you what to do. If you have an interest in physics, then if you read something and you don't understand it, if you have an interest, you won't just sit around and give up. You would do something because doing that is fun. If you do what you like, you'll do whatever, you'll contact these many people, you'll do this, you'll do that, because the motivation is internal. Whenever your motivation is internal, obviously jo cheezein hongi, they're going to be much better, they're going to be suited to you. And that's why self-learning comes in this if this is the circle of motivation internally, this will be the circle of self-learning. And other things about contacting people, about making connections and doing research, all comes within that sphere of interest. So if you develop an interest, you can do whatever you want. But in my particular case, what I did was, मेरी जर्नी तो सिंपली स्टार्ट हुई थी दैट आई वाज इंटरेस्टेड इन फिजिक्स. मैं इधर गया, मैं सर्न गया था बस. उसके बाद आई रियलाइज दैट आई हैव टू नो मैथ्स टू अंडरस्टैंड फिजिक्स. उसके बिना आई कांट अंडरस्टैंड फिजिक्स. सो आई पिक्ड अप my sister was in grade 10 back then. I was in grade 8. So I picked up her grade 7 actually, whatever, I don't remember, but I picked up her physics maths textbook of grade 10, and I started reading that when I was in 8th or something. And then I still remember, I didn't even know how to solve like x plus 5 is equal to 0. I didn't know what x was, but I then spent the next 3 days and I managed to solve a quadratic equation. I still remember, x squared plus 5x or whatever. And then I solved that equation because I was interested in the subject. And then my journey just started building up. I can actually show you my bookshelf if you want. I'll tell you which books I bought when. And some of the books I still have, like from that, like 4 years ago, and I still haven't read them. But the key thing is, okay, you should read the books. Aisa nahi hai, don't read them. मैंने इसलिए नहीं पढ़ी because I was too overconfident that I'll understand. But the thing is, those books help me understand कि मुझे कितना आता है कितना नहीं आता. Because I purchased those books because I wanted to learn something, and my parents never stopped me from doing that, and that's why I'm so grateful to them, to helping me follow my passion. And then what happened is, in 11th grade, so I should stay off the bat, I do not do theoretical physics research. I mean, I do research in that, but I'm not even close to the amount of knowledge you need to do that properly, because it will take like at least 4-5 years to get to there. Currently what I'm doing now in the Wolfram project is मैं बहुत lucky था कि I can explore all this stuff. And even if I get to like be in meetings, colloquiums, I get to see the developments in the Wolfram physics project. And I have a lot of stuff to say about the Wolfram project. I'll come to that later. But the thing is, if you try and if it doesn't work, it will ultimately work if you like keep on trying. Like, I know that's a very cliche statement, but it is true. It is cliche for a reason. 11th grade में मैंने I thought I knew a lot about general relativity. I actually didn't know anything. I was just a pea in a pod. But the thing is, 11th grade में मैंने Indian professors को contact करा. I wrote them emails कि I am interested in your work, even though I didn't understand that their work. I was interested in general relativity. I want to do research, and I want to do something under your mentorship. Like, I must have emailed 120 or something professors. I'm not even kidding. I emailed um not 120, that's a bit of a large number, but around 90 ke aspas. I emailed some foreign US ke professors as well. I emailed Indian professors, but obviously neither of them responded, because now I understand how bad I was in physics back then. And I was not even asking for a learning opportunity. I was asking for a research opportunity because I was a bit overconfident. So first of all, one piece of advice: there's a lot to learn. Always start learning and then do something like research based or something. So yeah, don't hesitate to contact people. The worst thing they can do is say no.
Yeah.
And the best thing they can do is say yes. So if yes, then everything is great. And if they say yes, ask them for a learning opportunity. Because they have so much experience in their field, they can tell you anything like you ask. So yeah, that's how I got in touch with people.
And I believe that's how you got in touch with even Wolfram, I guess. So can you explain a little bit more on Wolfram as to what Wolfram is? ये Stephen Wolfram कौन है? Why he's considered to be someone like a genius person in the physics, at least in the physics community, not if not in the science community, at least in the physics community. So can you explain?
So Stephen Wolfram is a genius outside the physics community as well. Like his whole theory is based on the theory of cellular automata, which is a topic in computer science and like math. And then he's also doing some stuff with economics in the Wolfram Physics project. Then also something related to philosophy. So he's just like another level 100 human being or something. But let me tell you about how I got the opportunity to be in the Wolfram Physics project. So in 12th grade, obviously 12th is for building your college application. तो मैंने अप्लाई करा वुल्फ्राम समर कैंप. वुल्फ्राम समर कैंप एक 2 हफ्ते का प्रोग्राम होता है where you learn the programming language called Mathematica. And in the first week, दूसरे हफ्ते में स्टीवन वुल्फ्राम तुम्हारे साथ वन ऑन वन बात करता है, and he tells you based on your interests what project will be suitable for you. And he is mentored like I don't know how thousands of children using his summer camp. Every year there are about 50 people. In my year, last year there were about 45, but this year there were about 50, and many of them are from India. So first of all, apply to the Wolfram summer camp because it is a really good opportunity. And you don't even need to know programming before. You just need to have an interest in a subject and you must have done something in it. So वहाँ अप्लाई करने के बाद I was interested in physics, and fortunately the Wolfram Physics project had just started. I applied in 2020 June, July, and the Wolfram project was just 6 months old by that time. So I was like, and they were looking for young people to mentor because 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 Wolfram is such an amazing organization that they really care about mentoring people, especially Stephen Wolfram. Stephen Wolfram has literally written like a whole essay on about how he finds mentoring. I sent it to you now. So yeah, and he I'll come to how amazing he is and how he changed my life. But other than that, after the Wolfram summer camp, I was not selected to be an affiliate with the Wolfram Physics project. But what I did was there was this Twitter. I joined Twitter, and on Twitter, the Stephen Wolfram himself post the affiliates, and I saw that I wanted to become an affiliate. So I emailed a bunch of people, and the people there are so good. They respond even though they know 100 times more than you, they definitely have so much humility that they will like give you opportunities. And so I was extremely lucky in that respect, and then I became an affiliate with them.
It's called Dunning-Kruger effect बोलते हैं उसे, जो knowledge versus your confidence level. Your confidence level drops as you increase
What
knowledge.
effect? I don't know that effect.
It's
Which
called
effect?
Dunning-Kruger effect. It's
Okay.
yeah, these couple of scientists, they came up with this concept and it kind of applies. सबके लिए apply होता है ये वाला concept, क्योंकि पहले आपको लगता है कि आपके पास जो knowledge है वो अच्छा है, बढ़ते जा रहा है. एक point ऐसा आता है जो 25% knowledge आपने सीख लिया, आपको लगेगा कि भाई मैंने दुनिया बना ली अपने हाथों में. But
Exactly.
जैसे वो 50% रीच होता है, आपको बोलता है अरे यार और भी सीखने का बाकी है, तो चलो और 75% में जाता है, तभी लगता है कि मैंने कुछ सीखा ही नहीं अब तक.
Exactly.
That kind of
Exactly.
feeling is there.
Exactly.
But it's a good thing. It's a really good thing कि आपने बिना किसी fear के, पहले बिना rejection के fear से आपने पहले लोगों को contact किया. आपने भले ही rejection हो ना हो अलग बात है, पहले आपने try तो किया कि आपने contact किया कि हाँ चलो ठीक है, let me just apply and see if I get into it. That's one major thing I think students will benefit understanding कि फर्क नहीं पड़ता कि तुम सेलेक्ट होते हो नहीं होते हो, बट एक एंट्री मारना चाहिए, एक पता करना चाहिए कि चलो मिलेगा कि नहीं मिलेगा करके. दैट्स अ वेरी गुड
Exactly.
पॉइंट. बट
Yeah.
ये वुल्फ्राम फिलोसफी क्या है, ये फिजिक्स प्रोजेक्ट का फिलोसफी क्या है? आर दे व्हाट आर दे ट्राइंग टू डू लाइक?
So that's it. Is that I can go on about like for 2 hours, because this is related to physics and then philosophy and then a lot of this stuff. Like I don't even know 1% of the stuff in philosophy, but still like
How would you
the
say
thing
that in
is,
5 minutes though?
I don't know that. Anyways, so okay, let me see where I can start. So the Wolfram Physics Project is not a traditional physics theory. What happens in a traditional physics theory is, like as I've explained in my book, Flex, sorry, but I was saying that a physics, how do you invent a physical theory? As I said, you observe the world with your eyes, nose, whatever, all your senses. Then you come up with patterns. And then you have and mathematics is like the best way you can express patterns. And then write down the pattern in a mathematical equation. The most famous equation being F is equal to ma, being Newton's famous equation. That is also purely based on patterns. He didn't wake up in one morning and say, oh, F is equal to ma. He did some experiments. He observed the world. He thought about the world. And then he developed a model that fits extremely, extremely, extremely well. But Newton's theory of gravity was just a model. It was not, it was a theory. A theory is something that doesn't, now people could say that, oh, it was theory. But the thing is a theory until it is disproven by something. Theory physics में तभी होती है when it is actually correct. मतलब जो भी हम experiments करते हैं, it is correct. But हमें ऐसे और experiments मिले 20th century में, 19th century के last में भी, I'll tell you about that later. कि that physics, that Newtonian gravity, Newton के जो laws हैं, they are incorrect, they are wrong. Specifically gravity का जो equation है, F is equal to G m1 m1 m2 over r square, that is wrong. And there were a bunch of experimental reasons. So what he predicted was Newton predicted कि you have a sun and you have planets that are revolving. He predicted very precisely what those orbits should be. But in the case of Mercury, what happened is Mercury's orbit is not is a bit weird. So what happens is, if this is the Earth and Mercury spinning around it, Mercury's orbit processes, right? So for example, what it means is एक center है जो sun है, and then Mercury is moving around it. But according to Newtonian gravity, it should move in a certain way. But gravity, Einstein की जो theory है, but what we observe actually, forget Einstein's theory, what we observe in reality is that the orbit is like this. It comes down, it goes over here, it goes over here. It's like the petals of a flower. It's the orbit itself is rotating about an axis. When the orbit itself rotates about an axis, it's called precession. And that orbit is precessing. And that is not predicted by, it is predicted by Newtonian gravity, but the correct amount of the precession is not predicted.
Okay.
So I forgot whether it is greater in general relativity or less. I don't know. But whatever, this was a wrong prediction. And so Einstein went along and figured out his own theory. But all of them figure out theories in the same conventional sense. They see something, they observe a pattern. Except in general relativity. General relativity is not based on patterns, but it is based on mathematics. But still, it is along the lines of physics theories. Even string theory, quantum physics, they all come from experiments, and then we do some math, and then we get the theory. But the thing is, in every theory, there are millions of assumptions. And those assumptions are valid in certain areas of space only. For example, Einstein's general relativity is not valid in high energy areas of the universe, such as black holes or galaxy formation or whatever. High energy areas of the universe where there's a lot of energy involved, the general relativity fails. And even string theory is not that promising in that aspect. Like, it has not promised any good results till now. The Wolfram project actually accepts that we can't predict anything from the start. It accepts that the universe is complicated. It accepts that there is something known as computational irreducibility. So it says that the universe is computational. Matlab, the universe is being evolved in a way that we can't predict. And the only way to predict it is to let the universe evolve itself. Okay. And so based on this assumption called computational irreducibility, that the rule of the universe that is evolving the universe is very complicated and we can't predict it. But जो theories हम निकालते हैं, but there is still a pattern to the universe. ऐसा नहीं है कि universe में कोई pattern नहीं है, इसलिए तो हम theories बना पाए. But the thing is, those patterns are only approximations. That's what the Wolfram Physics Project says. The deeper truth is something else. But जो current physics theory जो है, they do not see the computational irreducibility. They look for very small pockets जहाँ पे things start to make sense.
It seems like computational irreducibility in itself is like a separate topic to go into. It feels like nahi, it's something that Wolfram ka center point pe baitha hua hai. If Wolfram philosophy has to be surrounded by something, I think it will be focused on computational irreducibility. It feels like that.
I mean, if you want to get a sense of that, just read his book called New Kind of Science.
Okay.
It has everything about his like philosophy and stuff. But yeah, computational irreducibility, and is also known as the principle of computational equivalence, which is also like, it comes from computational irreducibility. So yeah.
You have also written a book on general relativity, right? जो वहाँ पे था curvature and geodesics, general relativity colon curvature and geodesics. ये आप why did you feel the need? पहला question तो ये होगा कि why did you feel the need to write a book when everyone else has also written, many of them, not everyone, many of them have written books on general relativity itself. Resnick Halliday हो गया आपका, बाद में H.C. Verma sir का भी था, उसमें mentions से general relativity के कई सारे. Why did you feel the need to write a book by yourself? Second thing is, what is geodesics? ये word नया लग रहा है.
Right. Okay. So first of all, this book is also a book on general relativity. It's written by Professor Thanu Padmanabhan, if that's the correct way to pronounce his name. I'm sorry if that's the wrong pronunciation. But he's an Indian scientist, and this book is one of my favorite books of GR, of general relativity. There's also this 1,500-page book on general relativity, written by 3 scientists. Charles Misner, Kip Thorne, and John Wheeler, I think. So, and that book is the most famous book in physics, if we could say. My book is not 1,500 pages long. It is 150 pages long. And so, and the reason why I wrote a book when there are other books that are not like 10 times in length, but also 10 times better than the book I wrote, is simply because those books are too complicated for a high school student. They are very good for graduate students, but they are very complicated for high school students. And even if I read that book right now, I won't even understand their book. So the thing is, I explained. So the reason I picked up general relativity is because I was just interested in like gravity itself. Like gravity was so fascinating, and it's different from, so there are 4 fundamental forces in the universe. If you boil every force down to four fundamental forces, it's the gravitational force, electromagnetic force, the weak force, and the strong force. In fact, when you touch an object, like if I touch this bottle, electromagnetic forces are interacting, but that's a separate story. The thing is, uh, um, gravity is so fascinating. That's why I took up this topic. And, and the reason why I wrote this book was that it has so many prerequisites. You have to have a complete undergraduate education to know that. But I wanted to write the book so that any high school student could pick up that book and get fascinated by the subject, so that they could actually read the book and see that they could actually understand the math behind the theory as well, so that they could understand how a physical theory is developed. So traditional books on general relativity go in a sequence that is not the same as what Einstein, developed. When he developed general relativity, he had a precise thought process in mind. Okay, ये है, इसलिए ये होना चाहिए, इसलिए होना चाहिए. I followed his thought process so that we can actually understand general relativity kaise aayi, why is it needed, and the basic foundation of general relativity in its mathematical glory also, because mathematics is where the thing it shines. It's a very elegant theory. In fact, I don't know if you've heard of these two physicists called Landau and Lifshitz.
Landau, yes, not the other person.
Yeah, Landau is more famous. They wrote a series of books, 10 books, which they called a theoretical minimum. I have his second book right now, and they are known for being incredibly terse. They are known for being very precise. मतलब कि वो एक शब्द फालतू का नहीं बोलेंगे अपने बुक में, बट उन्होंने अपने बुक में ऐसी चीज लिखी है जो उन्हें लिखा है, general relativity is probably the most beautiful of all physical theories, and they don't waste anything. So this really meant coming from them कि यार general relativity is really that beautiful. So that's why I wanted to pursue it. And when I was learning the subject, because I was interested in it, I found it really hard because I didn't even have the prerequisites in place. So after struggling a lot to learn the subject, I was writing the book side by side as I learned, so that another student could actually easily read the whole book in like a week and get enlightened that, oh, this is what general relativity is. And that's why I wrote the book.
That's really interesting. And actually that's really good of you that आपने एक बुक भी लिखा जो आपके समझ पे जितना आ रहा था आपने उतना एक मटेरियल बना दिया ताकि लोग सीख सके, जल्दी सीख सके. That's a really good thing. Geodesics क्या होता है वैसे? ये that thing, what is it?
Yeah, before I come to that, if you read my book, you won't even you will probably get a knowledge of like 2 or 3% of general relativity. That's it. But it tells you what general relativity is and what are geodesics, and why geodesics are a main part of the thing. So unfortunately, I do not have my basketball here, so I might have a hard time explaining what geodesics are. But imagine this. Imagine that you're on a road trip, and this is going to blow your mind. So let's see. So Newton says you have space, right? And I'm not going to give any of those trampoline analogies because I don't think they're particularly useful. But let me tell you what it is. Newton said that यहाँ पे सूरज है, यहाँ पे planets हैं, and they're revolving around. He said that एक force आता है which causes the planets to revolve in an orbit. And the force is like, it is the same force which keeps a ball on a string moving. It's called a centripetal force. That is the force required for an object to keep moving in a closed path. Okay? But here comes Einstein. He says that force is just an English word in the dictionary you can find. Hai kya force? Where is that force coming from? And the answer to where is that force coming from is where geodesics come in. So imagine that you're on a road trip and there's a mountain in front of you. So you're going to Shimla, just like two idiots went and picked up the third idiot. Right. So they go to there's a mountain, and the path of the road is curved, so it's spiraling around the mountain. ये mountain है, road path ऐसे जा रहा है. When जब तुम गाड़ी चलाते हो mountain में, not that I know how to drive a car. When you drive the car, you keep the steering wheel fixed. Okay, when you move on a surface, right, and if you keep your steering wheel fixed and just press the accelerator button, the curvature of that surface itself will cause you to move in that way, right? So on the road, however, you want to turn. Road पे आपको घुमानी पड़ेगी गाड़ी. But the reason is because the road is flat. The road has no curvature. But if you were to imagine yourself going around the mountain itself, अगर तुम mountain पे चल रहे होते, so there's a mountain and road उसके पास attached है. Remove that road. You're on the mountain itself, and then you fix the steering wheel and you press the accelerator and you move in constant velocity. When you move, the path you trace on that mountain is called a geodesic.
Interesting.
And that will, so you don't have an option of falling off because you're glued to the surface. And whatever path you follow by not applying a force, by the engine से कोई force नहीं आ रहा, कोई मतलब क्या बोलते हैं, you're not pushing the accelerator, you're moving in a constant speed. जो गाड़ी move करेगी mountain पे, that will be a geodesic. A simpler example is why flat earthers exist. Let me tell you why. Earth is curved.
That's a whole different debate, man.
Flat earth, the flat earth theory is technically is mathematically wrong, and I'm going to tell you why. The earth is curved. Okay, the earth is curved. You're standing on the ground and you're walking.
There it is.
ठीक है? The earth is a sphere because astronauts देख चुके हैं. ऊपर से earth एक sphere है. And if you stand on the earth and you move in a straight line, according to the astronaut who's floating above, you're not moving in a straight line. You're curving along the surface of the earth, right? But we always see that ये road सीधी है, तो हम सीधे सीधे चलते हैं. So imagine yourself starting at the South Pole, and then you press the accelerator in Antarctica, and then you move in a straight line. ये धरती है, you will trace this path. So if this is the North Pole, this is the South Pole. You will basically trace this path by going
Lines
straight.
of longitude वगैरह.
हाँ, you'll go through a longitude line. So you'll go through a longitude line, and according to you, at every step of the way, you will feel that the car is moving in a straight line. क्योंकि जब तुम zoom करोगे surface पे, तुम्हें flat दिखेगा. But then तुम गाड़ी चलाओगे, it will be like it's flat at every step. But on the macro scale, when the astronaut sees it, you're actually curving around, right? You went to the North Pole from the South Pole. And that's exactly how planets revolve the sun. The sun causes the space itself to curve, and the planets are moving in a straight line. But since the space is curved and the planets think they're going straight, they actually curve. Okay. And the curvature is similar to that on the surface of a basketball, because basketball पे अगर आप घूमते रहोगे, you'll eventually circle back, right? If you're moving from the South Pole to the North Pole, bend back. So imagine that as being the motion of a planet. And that's why gravity is the curvature of space, not a force. It's the curvature of space, and उस space की वजह से the planets are moving in so-called geodesics. And geodesics are basically straight lines. The definition of geodesics are straight lines, but they're applicable on curved surfaces as well. Okay. So planets move in straight lines on curved surfaces, and where planets move differently, the curvature is different. So yeah.
This is quite interesting, and the way that you explained it's a new perspective, because ट्रैम्पोलिन वाला जो एनालॉजी था कि हाँ तुम बास्केटबॉल ट्रैम्पोलिन पे डालो तो हाँ वो डिप हो जाता है, तो प्लैनेट्स भी ऐसा ही रिवॉल्व होता है. वो क्यों होता है करके एक क्लियर आइडिया समझ में आया है. सो फ्रॉम व्हाट आई अंडरस्टैंड इज दैट कि many students right now they would also love to have such explanation from our teachers, from our curriculum, to be honest. At least I would have loved to know that when I was doing my physics 11 years back. So where do you think from your perspective as a student who has been a student of Indian education system, where do you think our Indian education system could support such students who are really interested in this field, who are really passionate about such topics?
Okay. So I think books matter a lot. Your curriculum books, because I remember in my statistics book, there were these, my curriculum was the Cambridge curriculum. It was not the NCERT curriculum. So, and the NCERT is actually tougher than the Cambridge curriculum, but whatever. So the book is actually, I'll just show you 1 second. There are some excerpts in the book which I'd like to show you. I still remember where they are, which can really spark an interest. So let's see. this is the book I'm talking about, Probability and Statistics. And let's see. I don't actually remember um, because okay, right. This one, for example. See, so I'm reading a chapter about central tendency, which is this mean, median, mode, basic stuff. Then there's this excerpt in the book. Did you know? Right? You can see this. And then in this passage, interesting. Uh, they're telling some historical artifacts of mathematics and how Isaac Newton measured geographical positions. Interesting. Yeah, so stuff like that. In my book, fortunately, there were many such did you know things, and so I was interested. But that's just like 1% of the problem. I think teachers also matter a lot, because if teachers aren't themselves like motivating you to look at these things, you won't even bother in the first place. So I think it starts with teachers trying to make an effort to introduce the modern aspects of stuff, because often जो books में सिखाते हैं, the curriculum is good because obviously you can't understand the present day stuff without understanding the पूरा procedure. But to get fascinated, you need to know कि अभी क्या हो रहा है. And even the old stuff is really good, like mathematics or physics में जो discoveries Newton ने भी करी थी, they're also very fascinating. But a catalyst, if I would say, a catalyst to that procedure would probably be to introduce the current developments in the field, so that you could, as if the teacher does, then you can probably do that. And teachers have a lot of knowledge, right? I'm not saying that the teachers aren't good enough, but the thing is the goal of learning something is causing both the teachers and the students to hold back. The goal is to get good grades, and that's the only goal. The goal is not to learn, like it is to learn, but only to learn to get good grades. And we have to remove that. If that is there, then you won't bother to learn extra stuff, because your only goal will be ye exam mein nahi aayega, main kyun padhu, right? Because and students think that, and okay, so, and there's this paradox as well. If you read extra stuff, you'll get good grades, right? You won't have to work as much hard. In fact, you'll enjoy the subject. You won't have to do many assignments, and you can probably skip some homework. You can do extra stuff. You can buy books. You can interact with like people and make your life intellectually stimulating, and then still you can get better grades than other students who try to work as much hard, but unfortunately they haven't got a chance to do that. And so I was very lucky in that aspect, that I got a chance to visit CERN and do all that. But if someone doesn't get the chance, again, self-learning is a big thing, because the internet doesn't care about how much you get right in school. So obviously it's going to give you everything you want. Go to a Wikipedia article, वहाँ पे सब कुछ होता है, read it, and just go from there. To motivate myself, you can use this analogy to motivate yourself. There is something known as the Pavlov effect. The Pavlov effect is something that happens when you give a biscuit to a dog, right? So many of you must have pets, right? And then so the pet is sleeping, and he doesn't know, and he or she, whatever, doesn't know that you're coming. So, and then तुम किचन में जाते हो, dog वहां बैठा हुआ है तुम्हारा, and your dog hears your footsteps, right? And then he anticipates that, okay, my owner or my whatever is coming, and he is going to give me a biscuit. And then he gets excited, he starts wagging his tail and whatever. So that's how learning should be. You should be excited by the stuff that you don't know. If you don't know something, you think that, okay, now this is an adventure, मुझे ये पता लगाना है, and मैं पता लगा के छोड़ूंगा, मैं करके ही रहूंगा. And then you go on a Wikipedia binge, right? You go to Wikipedia, and then it's like a journey, right? So you go to one page, and then you see, okay, I'm here now, and 5 hours later you're somewhere else. And then you go back and try to learn stuff, and through the procedure you've actually learned so much, because you went somewhere else entirely. So if you want to learn about, let's say, planets, there can be a Wikipedia link which goes to like finance. You can end up learning something about finance as well. So that's the beauty of the internet.
Rabbit hole. It's a rabbit hole.
Exactly. Go to the rabbit hole, but you won't get stuck in the rabbit hole. The rabbit hole is like a U-turn. Niche jaoge, you'll eventually come back, and end up with so much information.
Maybe you might
So
learn a little bit about wormholes as well, I guess.
yeah, that's a good
Process.
analogy. A nice
Yeah,
joke. Yeah.
that's a really good thought, Utkarsh, and that's something. But apart from that, apart from self-learning, this thing, what sort of resources do you think that our Indian education system can provide for the kids,
Oh,
for the students? What do you think apart from just the self-learning motivation? Because a little help from other people can go a long way.
exactly. That's a good question. Sorry, I didn't answer your question before. I kind of digressed a bit, but let's see. What can the Indian education system do? Do you have some suggestions? I mean, let's see if we can come
Mm,
up with a solution.
So I thought about having open courseware from the university itself, like like MIT.
MIT Open Courseware, yeah.
Yeah, MIT has its own open courseware. IIT has its own NPTEL website.
nptel.ac.in, yeah.
Yeah. Those are क्या बोलूं वो advanced है, बहुत advanced level है. We need मेरे हिसाब से तो ये लगता है कि जब मैं पढ़ रहा था I would have preferred more practical hands-on experiments from the teachers, ताकि मुझे समझाए कि हाँ लैब जर्नल फिल करने के अलावा तुम्हारा काम भी ये है कि तुम एक्सपेरिमेंट खुद बनाओ, कुछ इनोवेट करो. क्या इट डजंट मैटर व्हाट द रिजल्ट इज, फेलियर एक्सपेरिमेंट है कोई बात नहीं, बट तुमने क्या सीखा यू रिकॉर्ड इट. एक पेपर कैसे पब्लिश होता है, इसका एक्सपेरिमेंट कैसे करना है, एक पेपर लिखने के लिए क्या क्या जरूरत पड़ेगा. कि आई नो दैट यू हैव रिटन 2 papers ऑलरेडी व्हेन यू वर इन योर 12th.
One. All right.
Two, right? With Wolfram you have 2 papers available in archive, I
No,
suppose.
no.
Maybe it's
I
one.
have I have one paper, yeah. Not
Yeah, so you have already done your bit of doing research and writing a paper, which is already a big thing in the scientific community, right? So I would suggest an exposure to something like that would actually be very helpful. मेरे हिसाब से तो वही था. So
okay.
that's an example from my side. Maybe you have something to add on.
I think your example is like perfectly valid. I think like open courseware are a good idea, but on the fact that they're too advanced. So the thing is, in any US university at least, and UK universities don't have an open courseware. In every year, US university पहले 2 साल तो basic पढ़ाते हैं, like not पहले 2 साल, पहला एक semester, sorry, basic पढ़ाते हैं, and the courses for the freshman year, मतलब जो पहले साल के courses होते हैं, they're high school level, like a bit more than the high school level. So MIT Open Courseware पे बहुत सारे courses हैं जहाँ पे you can learn calculus, for example. मैंने वहीं से सीखा था. MIT Open Courseware was like the Bible for me during high school. So for example, क्या बोलते हैं, कैलकुलस जैसे इंटीग्रेशन डिफरेंशिएशन, ये सब हमें स्कूल में पढ़ाते हैं. इफ यू हैव अ रियली गुड टीचर, they can teach you like anything. They can tell you that why integration was invented, why differentiation was invented. In fact, differentiation and integration both came when Newton was trying to discover gravity. Anyway, so integration and differentiation कहाँ पे invent हुआ, कैसे हुआ, and then what is the history behind it, in fact, a key suggestion, studying the history behind something is very useful, and you should definitely explore that. So अगर Indian education system में if your teacher is good, then it makes a really really big impact. But उसके अलावा I think self learning was like, for me it was 99% of the solution, because school में ऐसी चीजें होती हैं which you just can't do. For example, labs, like I personally didn't want to do any experiments because I wasn't interested in that area. I should have been actually, but I was more on the theoretical side. But if you want to do, like, let's say some experiment or something, if you can't experiment, then buy a book on experimental whatever, chemistry, biology, physics. Read that book, do the theory part. When you go to university, wait for a lab or something. I think you need to find your own solutions at some point. You can't rely on your school that much. In fact, the reason why universities are a good place to learn is because 90% of the learning there is independent. Even teachers know that. They acknowledge that ये तुम्हें खुद से सीखना है. We can't tell you anything. So in terms of the Indian education system, what can be done is, I think student clubs are really important. In
Okay.
student clubs, in my school, for example, there weren't many clubs, but in your school, try to start clubs and try to get students involved, because according to me, the more independent your education is, the better it is. Teachers are there to mentor you and guide you, but they can't teach you everything, because knowledge is like extreme, like this
I
much.
understand.
Teachers can teach you this much. It's up to you to learn the rest. And that's what my maths teacher used to say. And she was a really good teacher, and she was actually also helped me a lot, you know, getting my interest in mathematics. And if you find a teacher like that, which are there are plenty, just go to them, talk to them regularly. For example, when I was in 6th grade and I watched a documentary, like in 7th grade, I had this teacher named Anup sir, and I used to walk up to him every single day and just used to talk physics to him and talk physics with him. And then he would like just tell me like, buy this book or read this or something. And yeah, it helped me go, like it helped, just talk to people, you know, people are a really good resource, like, yeah. So
That's a
that
well put point. That's a well put. People are resources and they can't be replaced. That's a really
yes.
good point. And on that note, I would prefer to wrap it up here, the section 1, and we will move to section 2 part with Q&As and from the chat. I'll hand over to Miss Namrata, and maybe she will be able to access it from here.
Hi, Utkarsh, and thank you so much for such a nice podcast and such a nice views. So from here on, we will take on the Q&A session, like the question posted by our audiences, if on both on Zoom Live and YouTube.
Mhm.
So here we go. So the first person who want to ask the question is Parul Singhal, who is a curious parent and love to talk to Utkarsh. So Parul Singhal, please, can you come on?
I think access.
Uh, yes. हाय उत्कर्ष
Hello.
बहुत अच्छा लगा आपको सुन के एक्चुअली ऐसा लग रहा है कि हमें वापस से स्टूडेंट बन जाना चाहिए एंड वी शुड लर्न अ लॉट ऑफ थिंग्स क्योंकि मैंने कल का भी पॉडकास्ट अटेंड किया था और बाय चांस जो स्पीकर थे समहाउ मुझे एक ऐसा विजन लगता है कि आप शायद उनके बोलते हो ना उन्हीं के एक वर्जन हो पास्ट वर्जन हो जो हर एक चीज को बहुत एक अलग तरीके से देखते हैं जितना उन्होंने हमें बताया था एज अ ऑडियंस में इतना ज्यादा फैसिनेटेड हो गई थी उनसे बात करके कि उन्होंने बोला था कि वो हर एक चीज को एक्सपेरिमेंट करके देखते थे कोई भी बुक है तो नहीं वो कुछ भी 3D मॉडल बनाएंगे स्ट्रॉ पकड़ेंगे स्ट्रॉ से कुछ करके देखेंगे उससे शेप्स बनाएंगे एंड देन फाइनली ही विल रीच टू द आंसर तो ऐसा लगता है कि हाँ आप भी एक ऐसे पर्सन हैं तो मेरे को बस एक चीज ये जाननी है जो मैंने यूजुअली नोटिस की है इंडियन जो हमारे बच्चे होते हैं कि थोड़ा सा एक ना लोगों को कांटेक्ट करते हुए कि एक रिजेक्शन का डर होता है कि सामने वाले ने अगर हमें ना कर दिया या फिर हमारे क्लास में हमारे टीचर ने हमारा कोई कॉन्सेप्ट है उसको हमें डांट के बैठा दिया और हमारा वो कॉन्सेप्ट क्लियर नहीं किया या फिर हम लोग सेल्फ लर्निंग के अंदर गए ठीक है हमने यूट्यूब वीडियो देखा है बट हमने किसी को कांटेक्ट किया सामने वाले ने नो कर दिया तो हम लोग क्या करते हैं वो सेल्फ स्टीम पे लेके और अपना रास्ता छोड़ देते हैं तो व्हाट डू यू थिंक अकॉर्डिंग टू योर एक्सपीरियंस कि अपने इंटरेस्ट को हर एक रिजेक्शन के बाद भी आप कैसे मेंटेन करते हो ऐसा तो नहीं है जब आपने बताया है कि अराउंड 90 बोलते हैं ना लेक्चर्स को प्रोफेसर को आपने कांटेक्ट किया तो सबने तो हाँ नहीं किया होगा आपको मे बी किसी ने किया होगा बट आई एम सीइंग कि आप बहुत कॉन्फिडेंट है आज के टाइम में फिर भी सो हाउ टू ओवरकम फ्रॉम दैट कि एक बच्चे के पर्सपेक्टिव से
ओके बहुत अच्छा लग रहा है सुन के। आई थिंक वॉइस एको हो रही है, आप म्यूट कर सकते हैं। थैंक यू। तो बहुत अच्छा लगा आपसे सुन के, थैंक यू फॉर आस्किंग। तो हाँ, कॉन्फिडेंस के बात पे तो मतलब सबसे जरूरी बात है कि रिजेक्शन रिजेक्शन तब होता है when you get a formal email from someone that you aren't good enough for us. That is called a rejection. For example, I was rejected from MIT, Caltech, and other universities. But regardless, that is called a rejection. And you should be afraid of that. There's nothing wrong, human nature. But if you're trying to contact someone, they won't be as rude. Humans aren't rude. वो ये नहीं कहेंगे ये तुम्हें ये कुछ नहीं आता, तुम ये वैसे हो. They won't say anything like that. And so, and अगर उसे हम उसे रिजेक्शन बोलते ही नहीं है, हमें रिजेक्शन बोलना भी नहीं चाहिए उसे. अगर वो रिजेक्शन नहीं होगा तो सेल्फ एस्टीम या उन चीजों की कोई बात ही नहीं है. थिंक अबाउट इट लाइक दिस, योर गोल इज टू डू समथिंग and you have to do something, whatever, right? Regardless of whatever happens, you can do that. And I understand everything. Like for example, जब मैंने वोल्फ्राम फिजिक्स प्रोजेक्ट ज्वाइन करा था, मुझे भी देख के पता चला, मुझे झटका लगा कि मुझे कुछ नहीं आता. I don't know anything compared to these scientists, and it's nothing to feel bad about. In fact, मुझे पहले बुरा लगता था कि मुझे कुछ नहीं आता. और जैसे अभिनव ने बोला था कि तुम्हें लगता है कि तुम्हें इतना आता है, फिर तुम्हें लगता है कि तुम्हें कुछ नहीं आता. ऐसे सबके साथ होता है. बट तुम्हें अपने दिमाग को ट्रेन करना चाहिए कि नहीं, ये मेरे लिए एक्साइटिंग है. मेक इट एन एडवेंचर. And the thing you were talking about, the straws and like that experiments and kind of stuff, the reason why people do experiments, the log experiment इसलिए करते हैं ना, because they want to do something that they have not seen before. That's the meaning of adventure. You won't have an adventure if you've gone to Caribbean the Caribbean islands earlier as well. You would catch an adventure if you're going there for the first time. तो इसलिए learning को ऐसे बनाओ. Make learning a roller coaster which has ups and downs, but every one of those ups and downs are fun, right? Embrace everything. And first of all, मैं पहले ऐसा नहीं था, मैं बिल्कुल भी ऐसा नहीं था. I used to look down upon other subjects. So मैं physics पढ़ता था. I thought that physics is the toughest subject. I used to say that, oh, ये दूसरे subject biology ये क्या है? Like I used to say that. But in a world where everything is connected and knowledge होता है, knowledge is just like learning stuff. What's the harm in learning someone? And coming to the point of contacting other people, if you want to contact someone else, first you want to analyze why are you contacting the person. So if you want to, let's say, learn how to solve x squared plus 2x plus 1 is equal to 0, it doesn't really make sense to contact someone. You could go up on the internet and solve the equation, or you can download Mathematica and just type it out. But दूसरी बात यह है कि contacting someone doesn't have to do anything with how you feel. Contacting someone is also not to get a favor out of them. अगर तुम किसी को contact इसलिए करते हो कि तुम्हें कुछ उनसे काम निकलवाना है, if you want to do something, if you want a favor from them, then it's a wrong point of contact. You should. Stephen Wolfram actually said in one of his Q&A sessions, he also has a very good Q&A session, and you should actually check that out. He has a Q&A session for kids, and he does that every like 2 or 3 days. So I encourage that you tell your children and to actually watch those Q&A sessions. They are very, very good, and he knows like literally a lot about this stuff, so he can tell you. So the thing is, contacting people doesn't have anything to do with how you feel. You should only contact people if you want to have an interesting intellectual conversation with them. Then if they reject you, you won't even feel bad, because the original purpose to contact that person was to just have an interesting conversation. It was not to get something out of them. If, for example, someone refuses to give you a letter of recommendation, अगर वो तुम्हारे लिए LOR नहीं लिखते, then you can get sad. But if you want to contact someone to learn something, then you don't feel sad, because the goal was to not get a favor out of them, but just to learn. And so according to me, the solution to all problems, confidence, self-learning, ability to do things, experimenting, all of this comes in one thing that is called your interest. अगर तुम्हें उसमें interest है, तो तुम कर सकते हो. And that's what I've noticed, and I've been lucky to notice with my other friends as well. So in the Wolfram Physics project, I have a really good collection of friends, and they're from different countries. One of my friends is from Germany, one of the friends is from Russia, and they all kind of tell me the same thing, that they do stuff because they're very excited about it. Everyone does stuff because they're excited about it. The first thing you need to do is find something that you're excited about. Uske baad everything will fall in place. That's my answer.
And maybe उसके लिए you need to try out a little bit everything and then see कि तुम्हें जो पसंद है नहीं आ रहा है, try करने के बाद ही पता चलेगा whether you are interested or not. Then you can move forward.
Yeah,
Just wanted to
read,
add that
watch
in.
documentary, देखो, read and just like enjoy every step of the way. ये मेरा suggestion.
Okay, thank you for the question, Parul. And we move to the next question. It is from Miss Parmita Chaudhary, and she's teacher of chemistry. Ma'am, please go on. Miss Parmita Chaudhary, are you there?
I think in the
Okay,
Zoom
we
meeting,
Okay, we can take her question later on.
I have asked
The
to
next,
unmute her. I'm sorry, I have asked to unmute her, so maybe she can access it now. Maybe she's not able to access.
okay. So the next question is from Kanika Roy, and she is Masters in Physics from Guwahati. Kanika, please go ahead.
Good evening.
hello.
So, Utkarsh, like after listening to you, seriously, I didn't learn so much in my masters. The way you have like explained things, they are really practical, and I'm really amazed with it. So, I want to know what kind of research are you doing there? Because in the last year, I have completed my masters, so I'm moving towards PhD. So,
Oh,
I'm applying
congratulations.
abroad. Oh, thank you so much. So I'm applying abroad. Basically, I am working in biophysics.
Interesting.
So I am applying abroad, but I am not getting positive responses. So I don't know how to really approach the people. So can you just guide me on this?
Sure. I think I can. I asked one of my mentors at the Wolfram Physics project. I think they're open to actually taking more people. So I can definitely put you in touch with them, and maybe you can also join the program. They're definitely looking for more people. Right. What was your question again? What research
Like
am I working on?
Yeah, because I have worked in 3 projects. Like 2 were theoretical physics, and the last one was from IIT Guwahati, that was in biophysics. So
Oh,
I'm open to both the things, like experimental more, like I'm more inclined towards experimental one, but I too like modeling and all those things. So that's why I asked you. Yeah.
sure. Well, I don't know much about biophysics or experimental physics. So currently, the research I'm doing over there is purely theoretical. And currently, in the Wolfram Physics project, there haven't been any concrete developments in the experimental physics uh, line, because we don't know what experiments to do in order to test the Wolfram theory. Like, it's not exactly a theory,
Yeah.
but
Yeah.
in the theoretical project I'm doing, I did one project earlier, which was not related to the Wolfram Physics project. It was about special relativity. So in special relativity, the Lorentz transformation is a measurement. So what happens is that if you want to measure the length of an object, you have the meaning of length in special relativity is when in different reference frame you measure the length of an object. But the reason why the length is different in different reference frames is because the notion of simultaneity is different in different reference frames. So according to the moving observer, two events will not occur at the same time, but in the stationary frame they will occur at the same time. So both the observers are making the measurements of the length at different times, which is why the Lorentz contraction happens. What I investigated was that what are the visual effects of the Lorentz contraction, and basically if any object is moving and there's a camera in front, how would that object look like? So that was my research, and the people at the Wolfram Physics project guided me through it. It was mainly about the visual appearance of extended objects that execute rigid body motion in special relativity. Currently in the Wolfram Physics project, there are like tons of projects I can do. I have chosen one right now, which is on non-inertial frames in the Wolfram Physics project. So in the Wolfram Physics project, the Wolfram Physics project is very much related to something known as causal set theory. Causal set theory is another area in physics, which is another theory of physics similar to string theory, but it is not that famous. But it just assumes that space-time is discrete, not continuous. So instead of like there being points everywhere, there are only a discrete collection of points, and that is like the basis of the Wolfram Physics project. And so I am currently investigating how special relativity and different relativistic effects occur in the Wolfram model in their description of discrete space-time. So I give a demo, actually. I think I'll give a demo in the third section, and I'll explain more on the Wolfram Physics project and like what discrete space-time really is and so on, and how it came to be. But yeah, I think currently I'm just working with relativity in the Wolfram Physics project because I do not know much quantum physics, but I do know relativity. So I'm exploring that.
Okay, thank you so much.
Thank you, Kanika. And the next question is from Yorick Zeske. I'm so sorry if I got the name wrong, but he has a very nice question. The question is, self-learning is probably very effective when the students have the motivation and teachers who can inspire them to do it. Still, how you can think, could we give more student motivation at the large scale? This is a YouTube question.
Right. So shout out. He is one of my friends in the Wolfram Physics project. He is another junior research affiliate, and you can probably invite him to do a podcast as well. So he is currently studying in the Netherlands, and he's doing a lot of exciting work in maths. And currently he's learning subjects other than the STEM subjects. So that's pretty interesting. His question is really good, and I didn't anticipate a really like a good question from him. So right, interesting. So self-learning definitely is not fundamental in the sense that it requires a kick from either something else. So it can be a sentence uttered by your teacher, which is really fascinating, or it can be something that you come across. In my case, I came across this documentary by Brian Greene that is on the fabric of the cosmos. So that motivated me, and yeah, and I think going to CERN was also one of them. So on a large scale, that had, for example, this organization is one of the organizations that is trying to do that exactly. So I think the goal for that is a change in culture itself. What I mean by that is, in the US, the school system in the US is very different. So over there, what happens is that students learn more independently in schools than people do here in India. So in the US, they have a lot of clubs, student clubs, and that's why the university system is pretty similar to the school system. And that's why Indian students face a lot of problems transitioning to US universities. And I think changes to the Indian education system is definitely going to be, if not like, is going to be one of the solutions to promote, to give student motivation on a large scale in India. I do not know the system in other countries, but in India, I think I think first of all, technology is really important. Many people do not know how to use technology correctly. They do not have access to computers. So I think in schools, definitely good internet connections are required. And what I mean by that is, I think we need to enhance it technologically, and everyone should get like a PC or a laptop or something. And if they can't afford it, they can use their mobile phones to do like all sorts of interesting things. So I think the motivation behind self-learning itself can yeah, I think you're right in the sense that it has to come from something. I do not particularly know how, because I came by the documentary by accident. So I would say um, hope to come across more accidents. That doesn't really make sense. One of them could be visit interesting places and keep and read a lot. I think one of the things is reading. If you have a habit of reading, like even novels, you'll probably read something else, and you can come across that. So on a large scale, I think it's just as we advertise for clothes and stuff, we can probably advertise for this too, like books and other things. Instead of movies and cricket in India, we can advertise for edX or Coursera. So yeah,
Maybe a bit of YouTube can help a lot. I mean, instead of
TikTok,
no.
yes.
Instead of shorts, instead of 15-second videos,
Yes.
maybe just put some podcast at the end. Put toss podcast, that's also free.
Yeah.
But just kidding. You can put any podcast at the end and just let it run in the background. So, it's a way of subliminal messaging. So that can be done.
Mhm.
Okay, so we get back to Pamita. Pamita, if your network allows, can you come and ask the question? Pamita Chaudhary. I think she has some network issues.
I just sent a message to him saying, nice question. Anyways.
Okay, so I think Pamita is not able to join. And the next question is again from Parul Singhal. Parul Singhal, come on the floor and ask the question, please. Parul Singhal. Parul Singhal, can you hear me?
Yes, ma'am. I can hear you.
Okay, please go ahead. Go ahead with your question.
Yeah, just a minute. तो जैसा मैंने अभी उत्कर्ष से सुना और जो कल के सेशन में सुना था, सो इट्स लाइक कि हम लोग कोई भी चीज होता है, हमारी जो फर्स्ट चीज होती है, हम लोग जो सबसे पहले शुरुआत करते हैं किसी भी थ्योरी को बनाने के लिए, तो होती है ऑब्जर्वेशन. ऑब्जर्वेशन से हम लोग पैटर्न्स डिसाइड करते हैं, पैटर्न से हम लोग फिर समहाउ थ्योरी बनाते हैं. लेकिन ये जो सफर है, दिस इज नॉट कि बहुत छोटा सफर नहीं है, ये बहुत बड़ा सफर है.
Utkarsh, I will take over her question. So according to her, she was trying to say that observation से pattern और pattern से theory बनाने का सफर बहुत लंबा होता है, and you need yourself to be keep motivated for that because there are lots of failures in that. So according to you, how scholars are managing this, like how they are doing it, who are successful one, and maybe there are some failures which were ought to be give us a great theories. So but they didn't keep motivated in that way. So what's the point, like how scholars can be keep motivated for this so that they can go for observation से pattern और pattern से theory, इतना लंबा सफर तय करने के लिए, how to keep them motivated?
That's a good question. But the thing is that luckily we can collaborate with other people, because this journey, like, yeah, like developing a theory, for example, general relativity took 400 years. It started in 1600s by Newton. He observed some things falling to the ground from a tree, although that's not true. Then then फिर उसने मतलब experiments हैं, मतलब उसने experiments किए. He talked to other people. He exchanged notes with Leibniz. And then this whole calculus battle, ये मतलब battle चलता है कि किसने इन्वेंट करा था कैलकुलस, न्यूटन ने या लाइब्निज ने. बट एनीवेज, पिछले जमाने में जब एरोप्लेन ट्रेन नहीं होता था, तब वो लेटर से एक्सचेंज करते थे और थ्योरी साथ में बनाते थे. तो अभी अगर आप देखोगे कि कितनी मैथ्स की नॉलेज है, अब इफ यू पिक अप अ मैथ्स टेक्स्ट बुक एंड यू सी द अमाउंट ऑफ स्टफ इज इन देयर. There's a theorem by Leonard Euler. There's a theorem by Ramanujan. There's a theorem by hundreds of other mathematicians, and it takes like thousands of humans to come together to create a theory. So obviously one single person won't develop his or her own theory. And in physics today, there are only a limited amount of theories that are well accepted by the society. For example, there's string theory, loop quantum gravity, causal set theory, as I said before. Then there are other versions of general relativity, such that, for example, I forgot the name. It's in this book, but whatever. And then, yeah, there are so many other theories in physics. So, you know, you don't have to develop a theory yourself, and that's where other people come in, and that's where the process won't take as long. Because क्या है कि there's a reason कि अभी scientific advancement कम हो गई है पिछले जमाने से. कम तो नहीं हुई है, but it has reduced because the low hanging fruit has already been plucked, right? Because जो पहले जमाने में discoveries हुई थी, they weren't discovered yet, obviously. So someone had to discover them, and now that they've been discovered, we have to progress. And now there are problems in physics that are very hard to solve, like quantum gravity, for instance. And these problems are so hard to solve that everyone knows that we can solve them, but we don't have to do the theory from start because that has already been done. So from observation to experiment to that, no one has to do this like now, because every theory has been developed. If you want to start a new theory, you build on existing theories, because existing theories are correct because they're tested with experiments. And that's what the Wolfram Physics Project does. It claims that other theories are approximations to the actual physical theory. And that is like a test for, that's like a test for the theory itself. For example, general relativity is tested when the speed of light goes to infinity. When the speed of light goes to infinity, the laws of physics reduce to Newtonian gravity. When you take the limit of the geodesic equation, it reduces to the Newton's acceleration of free fall. So yeah, now no one has to do any observation to experiment to that. We have already done that. Now is the golden era of science where it's like a make or break situation. हमें पता है कि what is wrong with the theory, हमें पता है what is correct. Everything right now is about passing that barrier. And once we do, then much of the problem is solved. So right now we don't have to worry anything about worry much about observation, experiment, theory. And collaboration is definitely one of the key aspects of this.
Thank you, Utkarsh. I really love to hear that. Matlab, it's just now increasing my curiosity toward the subject. Thank you so much. मेरे को एक और क्वेश्चन था, जैसे आप अपना ये बता रहे हो, तो इसमें आप एक टर्म यूज कर रहे हो, न्यूटोनियन ग्रेविटी. क्या आप उसको सिंपल लैंग्वेज में थोड़ा शॉर्ट में मेरे को बता सकते हैं कि व्हाट इज दैट? बिकॉज आप जो एक्सप्लेन कर रहे हैं उसमें एक टेक्निकल टर्म है, एंड आई एम नॉट फ्रॉम साइंस बैकग्राउंड, सो just curious to know this.
So Newtonian gravity is just the theory of gravity which was developed by Isaac Newton in 1666, I don't know, but Newton ने gravity का original idea उसने डाला था कि gravity एक force है, and उसने एक equation बनाई थी जो बताता है कि अगर आपके पास दो चीजें हैं, उसके बीच में जो force होगा, उस law को हम बोलते हैं Newton's law of gravitation, और उस थ्योरी को हम न्यूटोनियन ग्रेविटी कहते हैं. जो जनरल रिलेटिविटी जिसकी मैं तब से बात कर रहा हूँ, वो आइंस्टाइन ने इन्वेंट करी थी 1915 में 16.
Okay, so actually I have so many questions in my mind that I can call you separate if I will get your number. And I can ask you so many questions later on.
Sure.
Thank you so much. Thank you so much for your answers. Thank you.
No problem. No problem.
Okay. So thank you, Parul. And Utkarsh, next question will be from our techie who's looking after all the technologies and Zoom and YouTube, everything. So Revan, please go on. You can ask the question.
No, sure. So my question is relating to, like, other than physics, like what do you enjoy doing, like other than physics, or like basically your work that you're doing? And yeah, that's the first question. So the second question is, like, and what's the way forward that you look for, like think for yourself, like now that you're exploring physics, like with one of the best programs and like with one of the greatest minds, what do you think for yourself in the future now going forward? So two questions.
Sure. Great question. because I myself don't know. So, but anyways, the first part of your question was what apart from physics? Yeah, so in the academic side, I am mainly interested in physics, maths, computer science. And now recently I've started to develop interest in other subjects such as writing. I really was really bad at writing, but now I've actually learned from some people that it's important to keep your mind open and learn different things. So I'm trying to learn different like areas. Particularly, I'm interested in biology now, so I'm learning about the theory of evolution and other stuff. Okay, and then apart from like academics in general, I really enjoy like sports. So I play a lot of sports. I play basketball every day. I play table tennis a lot. I play let's see. I play golf sometimes, and then I used to play a lot of cricket. I was in the cricket school team, and yeah, I really enjoy playing sports. And then apart from sports, I think यही hobbies है मेरी. Sports is one of the biggest hobbies I have. Other hobbies I have are just procrastinating and watching YouTube videos, watching NBA videos on YouTube. So yeah, that's one of the things. And then other areas where I find interest is, I think history is like recently I started getting interested in history and like analyzing people itself. So I have I keep if there's some scientist who is really successful or even not that successful, I pull up his Wikipedia page and read histories and then compare them to each other, whether they're like similar or how are they different and all that. So reading history is also a lot of fun. There's this good YouTube channel called Epic History TV or something, and I forgot the name. So yeah, they have really good animations and stuff. So I watch that, and yeah, like yeah, that's it. And then about your question to move forward, yeah. So it's right now it's just like the start for me. There's so much to do now. Um, I literally just know nothing right now compared to what is already there, and I want to like learn so many different things. And for example, I want to do like a lot of computer science. I know computer science, but I want to do even more of it. I want to learn more physics. I want to do more math. So currently, I don't have a particular goal in mind that I want to become a physicist or whatnot, or do I want to work in CERN or whatnot. I do not have any goal right now. For the first 4 years of my college, I would just like learn a lot of stuff, and particularly a lot of mathematical areas such as mathematical biology, mathematical computer science, all that. And then just learning for the sake of enjoyment and stuff. And side by side, doing many projects as well for the Wolfram Physics project. And then I have a few side projects as well, just for fun. So I do not have a goal in mind that what I want to do. I probably should, but I think that I can decide that a bit later as well after the first 2 years of college. But for now, it's just like learning. So
Thank you, Utkarsh. And the next question is from YouTube, and it's from Nilakshi Nag. And she asked that how good idea is it to choose a research topic which is not so much in the trend? Some students don't choose topic as per their interest as it is not in trend. So what do you have to say about it? Again, to remind, Nilakshi Nag is a teacher in Agartala.
can you repeat your question? Your voice cracked. Like I think my internet is a bit slow now. Can you
Okay.
repeat the question?
Okay. I'm sorry. Nilakshi Nag, science teacher from Agartala, she have put in a question that how good idea is it to choose a research topic which is not so much in the trend? Some students don't choose topic as per their interest as it is not in the trend. So what do you have to say about that?
Um, I think at least in the school level, you can't. It's impossible to contribute something new, right? It's really like unless you're a genius or something, unless you've completed your PhD at the age of 14, do not worry anything about like this is in a trend or not, because I think you should like learn, because from my experience, when I did my research project about relativity, it wasn't particularly in the trend. Like relativity itself was known, but the thing is, I did something related to the visual appearance of relativity, and I really had a hard time doing that. I ended up writing a research paper and editing it like 1,000 times, wasting a lot of time trying to perfect it, and now there are more imperfections. The thing is, when you do a research, you shouldn't have any, because since you're just in school, it doesn't have it doesn't make sense to have like a goal of the research, first of all. And if it doesn't have to have a goal, it means that you shouldn't worry about whether it's in a trend or not. So if for example you're trying to investigate the effect of temperature on a reaction, on a chemical reaction, then instead of wondering about what things have not been done in this area, like finding some experiment whose effect on temperature isn't known, just do an experiment yourself in the school lab and try to just do it yourself. That's the best way to learn, and not worry about any output that you'll get. Because if your stuff, if whatever stuff you do is driven by something else, like an external motivation, this is an external motivation to get something out of it, before even doing that, is known as is an external sense of motivation. And you'll always, most of the times you'll fail, right? You won't be able to do it correctly. So again, according to me, the best thing to do is follow your interests and focus more on learning rather than contributing something new. Because, like, for example, I was fortunately part of ISEF. So ISEF is the world's largest science fair for high school students, and my project got selected for that. And even there, I saw that people aren't doing anything new. Like, they're just building on whatever's being done. For example, one project was about investigating the effect of air on tennis ball trajectories. That's related to Magnus effect and other kinds of physics things. And there were other projects. So right now, it's not even worth thinking about what is in a trend or not, because first of all, if you do that, research won't be as good. Second of all, you can't do that because you're just a high school student. Knowing what is in the trend and what's not in the trend is definitely very hard to do. So the solution should be, find something you're interested in, focus on learning, and then and if you want to research, treat learning as a research experience. Instead of reading the chapter, try to figure out that chapter by yourself. And then, yeah, so if you want to learn some chapter, try reading a summary of it on Wikipedia and trying to like jot down your thoughts and do something. That I will come to that in section 3. It's called computational thinking. And then you'll end up with the research opportunity itself. You don't have to worry about anything. You can't start with a goal. You have to start with something that is accessible, and then you reach that goal ultimately. That's the answer.
Thank you, Utkarsh. The next question is also from YouTube, and it's from Himanshi Singhal, and she has asked that what, according to you, what are the hottest physics problems in today's world? Hottest physics problems.
I do not know all of them because, again, I'm a high school student. Just as I said before, I do not know what's like always trending or not. To do that, you have to ask the experts. But on the surface level, I know that quantum gravity is definitely one of them. The theory of everything is one of the hottest problems in physics. And I think in section 3, I'll go in like some length about why we need a quantum theory of gravity and why general relativity and quantum physics do not work. And then I'll probably talk about that. But to answer your question, quantum gravity is one of the biggest problems in theoretical physics. I do not know about experimental physics. In experimental physics, I think recently some team measured a mass of a proton really accurately, and that's interesting. But anyways, so the most hottest topics in physics today is the theory of everything, the theory of the 4 fundamental forces in the universe, and that includes string theory, loop quantum gravity, other physics theories like the Wolfram Physics Project. And that is probably it's like the most trending topic right now.
Okay, thank you, Utkarsh. Thank you so much. And with this, we are at the end of the Q&A session. There's no question, but there is a query that if people over here want to connect to you for some kind of query and something or else, so how can they?
Sure. So I think I can give them my email address if that's fine. I don't know if it's going to be posted in the description or not, but like how I can give my email address or something. And we're also going to do the mentorship program, so that's another way. But in the email thing, I can give you my email address.
Okay, so we will post the email address in the chat box, and that's it for the Q&A session. I will hand over to Abhinav. Please take over the free flow session. Thank you so much, Utkarsh.
Thank you. Thank you very much, Utkarsh, for
Thank you for your
the
question.
answer. Yeah, the questions were pretty interesting, to be honest.
Yes.
And anyway, let's move to the section 3. And I think we pretty much were in the section 3, given that
Yeah.
it had a bit of free running thought process there. But definitely, yes. Let's officially move to section 3, where we can have complete free discussion. And I'm actually unmuting everyone, so they can have complete access on how they can question or network with you if they want to find out more, or you can network with them. It's completely flat hierarchy right now. So, but one question that I had in mind was the craziest anecdotes within physics. I know that you have been working for almost one and a half year with Wolfram. So what anecdotes do you have that you would love to share with us?
Well, anecdotes in like physics in general or my experience?
In with Wolfram physics that you have had, like in terms of research, or maybe in terms of interaction, or maybe with any other scientific community that you think.
Yeah, there are plenty of them.
All good stories start with that, actually.
Yeah. Let's see. Okay, the thing is, every week was almost every week, the Wolfram Physics Project has colloquiums. So, like, scientists from any part of the country who's interested in the project can come and speak on the work they think, the work they're doing, and how that can be related to the Wolfram Physics Project. So, we have had like many colloquiums, and Yorick, he was also one of the people who spoke in one of the colloquiums. I was also one of the people who spoke in one of the colloquiums, and yeah, so a colloquium is just a way where people come together and brainstorm. We present our work, and then people start brainstorming. So, and then we come up with ideas. The thing is, they are pretty crazy in a sense that a lot of new ideas are being generated like this, right? If you sit in one of the colloquiums, it's like, as my friend one of my friends in the Wolfram Physics Project, he's Russian, and he told me that it's like being in an athletic race. Stephen Wolfram is thinking so fast that you can't keep up with him. But it's so fascinating to see how people think, right? I mean, the way they approach problems specifically. So, like, the thing is, in a colloquium, when we present our work, then in the chat box, people start writing stuff like, okay, this is the idea I have, this is the idea I have. Then people start looking around, and then it's just nothing but 2 hours of pure intellectual discussion, right? That's also free flowing discussion like this. And that's like that's interesting, because I thought originally that physicists do research by just having a plan, right? Ye karna, ye karna, ye karna. But it turns out that restricts whatever you can do. Your maximum brain power is executed when
When you're free.
you in a free flowing discussion, and you're brainstorming, and you don't care about what's happening. You're just in the mode. You're just in the mode. I confused mode and zone, that's why I said mode. But you're like in the zone, and then you're thinking about all these interesting things. So that is one of the crazy things that happened in the Wolfram Physics Project. The other crazy thing that happened is the other crazy things that happen are is the way I get to talk to people. So I have been assigned 2 mentors. One of them is Xerxes Arsiwala, and second is Hatem. I don't know how to pronounce his last name, but they are really, it just fascinates me how people are so kind and so like physics is one thing. I think on an emotional level, I have more interesting anecdotes because physics I have yet to understand the stuff that is happening over there. It's really advanced. But and I'll come to the crazy physics stuff as well in a moment. But emotionally, the people over there do not care what your background in physics is, right? They don't care about what you know. Like as I said, I'm just a pea in a pod. I don't know anything. But still, they take a lot of their time out to mentor me and then other people as well. And the people over there are so good. If I ask them a question, we have a Slack channel. So on the Slack channel, we can interact with other people. If I have a question, I can just post it and then people will reply. And then there are just so many free flowing discussions that happen. It just fascinates me how the background or age of a student is irrelevant in learning, right? That's one of the crazy things that I think happen in a few treasured places like the Wolfram organization, where Stephen Wolfram is really the driving force behind, mentoring people and just doing stuff for the sake of doing it. And on the subject of Stephen Wolfram, I think Stephen Wolfram has completely changed my trajectory in physics, which is another crazy anecdote, just like CERN did. So Stephen Wolfram helped me with a lot of things. He helped me with my research paper. He took he okay. So the thing is, it's like a university. I can schedule office hours with him, and once I do so, he comes and he meets with me one on one for about 2 hours, and then I discuss about my project, and he gives me feedback. And then he gives me he gives so much feedback that it can be valid for the next year, right? The amount of work he can give me is it can be valid for the next year or so. एंड सो वहां पे वो चीज़ बड़ी अच्छी लगती है कि उनने अपना टाइम निकाला अपने बिजी स्केड्यूल से और मुझे मेंटोर करने की कोशिश करी. And also he replies to emails like in 2 days. If I want to send him an email, he'd reply back in 2 days. So definitely getting to witness the work of Stephen Wolfram is it's a privilege, and it's a really lucky opportunity. And I think I've gained a lot from him.
That's a really interesting one. Okay. Do you perhaps have any thoughts on what's the future of Wolfram right now, like in terms of its Wolfram Physics project, in terms of its ideas? Like, where do you think it's going in the future if people want to join?
I think the more people join and the more people collaborate, the better. I think this podcast is also, it can be used as a promotional way to get people interested in the project. And I talked to one of my mentors. He thinks that getting more people interested will be much better because the project is not that easy. The project is based on the fact that the evolution of the universe is unpredictable inherently. And so the mathematics involved is kind of difficult, like really difficult and high level. It isn't difficult for a mathematician, but yeah, it is a good theory in itself. And the amount of work that has been done in the Wolfram Physics project is enormous, but it's nothing in comparison to the amount of work we still have to do. The thing is, we have to come up with an experiment to test our predictions, and that seems like a long way, according to me. Like obviously, people who are currently working on it with full power is Stephen Wolfram. He can tell you more about it. But I think it is definitely moving in a promising direction because it is like not only physics, it is giving it has these branches to other areas as well. So for example, it has a branch to philosophy, which I'll talk about in a moment, and it has a branch to economics, it has a branch to biology, it has a branch to finance, because it can be thought of as like a computational model in itself. Like it's a different computational model. It's like related to something known as multi-threading, and it's a bit different. So and Steve Wolfram recently wrote an essay about it as well, so you can check that out. But yeah, I think there is a lot to do in the Wolfram Physics project. Definitely one of them is to figure out the fundamental theory of physics and to test our predictions. And the first step to doing that is to see whether theories in physics currently arise from the Wolfram Physics project. So I'll tell you why that should be the case, why relativity, quantum physics should come out of it should be emergent from the theory. And yeah, and then the second goal of the project is to just change the way of thinking about like mathematical related stuff. What I mean by that is Stephen Wolfram's book, A New Kind of Science, is like, as the name suggests, it's a new kind of science. It's based on not mathematics, but it's based on computation.
Mhm.
And I'll tell what that means. So and the Wolfram Physics Project is turning out to be something different. It's turning out to be a new kind of science. It's turning out to be like it's like totally different in a sense, building upon the new kind of science. So there's definitely a lot of stuff to do and a lot of exciting stuff that's to come.
That's okay. So maybe say 6 to 7 years down the line, 10 years down the line, you might be able to see that it has a concrete idea of the fundamental theory, at least the grasp of it computationally, don't you think?
Can you repeat your question?
Maybe say 10 years down the line, say 8 to 10 years down the line, given that more people collaborate, it's like a distributed community which is working on different pieces of the puzzle to make it. And
Exactly.
so maybe around 10 years down the line, do you think Wolfram Physics Project might have a very concrete foundation, so to speak, of fundamental theory? Do you think so?
Yeah, it has a foundation. It already has a concrete foundation. Like other theories don't, but this theory is based on the fact that it has to start from something. And there are a bunch of technical papers that have already been written, which are pretty rigorous, but they still have to be more rigorous. Many of the
Mhm.
claims, like the papers that have been written are more of claims, but they still need to be kind of proven. So that's an interesting thing. But yeah, they are pretty rigorous. I mean, they are like a lot of the stuff has already been proven. So yeah,
Mhm.
definitely 10 years easily. A lot of stuff would have already been done. And a theory, I think, yeah, 10 years is enough time to, I think even 3 or 4 years or like 5 or 6, I don't know. It's really hard to say right now. But yeah, definitely in 10 years, a lot of stuff will get, seeing the productivity of Stephen Wolfram, that's what I can say. And other people is that, yeah, a lot of stuff is going to get done.
Okay, that's pretty good. We have one question from YouTube which asks how to maintain the quality of research in academic institutions when we live in a very milestone oriented system. Like that could be the right question to ask, given that
Okay. Can you repeat the exact question?
how to maintain the quality of research in academic institutions when we live in a very milestone oriented system. So if we have, say, we achieve we have to achieve one milestone per year. So within one semester, एक paper तो publish करना है मुझे. That cannot be the goal. The goal should be that the quality of the research that we produce, irrespective of the time, needs to be a top notch. How do we maintain that?
That is a very difficult, it's a very good question, and that is a very difficult task. I'm not even close to achieving that itself. It depends person to person. So every person has a different system of achieving that. It can be different time management skills. It can, this answer really boils down to like it's kind of subjective. It depends on the person. So there are a few general things that can be said about this, but like motivation, passion, not procrastinating much, and doing work and all that, not thinking about the future and all that. It depends on person to person. So you have to have systems in place that help you achieve maximum productivity, and that can give you like the thrust to keep powering on even if you don't understand something. That is something personal, and you'll have to figure that out on your own. But I think that's yeah, I think yeah, you're right in the sense that it is a milestone oriented world, because if it weren't, then work won't be as, you can't get work done. So yeah, time limit is definitely a problem is definitely constrains your creativity in a sense that you can, if you have an idea at the last moment and you can't pursue it, it's unfortunate. But find a system so that you can pursue it after the thing, and probably you can incorporate it before. Like find some personal systems that work for you. I think that's but it's a really good question.
But at the academic institutions, if you look at it, most of the universities जो हमारे यहाँ पे भी है, they'll be like, हाँ हमारा कोटा है कि हम साल में 12 पेपर पब्लिश करना चाहते हैं, ये हमें फुलफिल करना ही होगा. तो क्या होता है कि when a person wants to write a paper, he'll be like, हाँ मतलब I want to write a paper this January, I want to publish it by March, I'll write in February, I'll publish it by April. So ये this अपने आप को इतना सेल्फ कंस्ट्रेन करके जो बैठते हैं, this is not a very conducive, very good environment for anything, like a subject to publish. And maybe people in the audience might be able to tell very clearly, because as I believe one of them have done their masters in physics, they might have seen have they experienced such
They
things.
can give a better answer than me, because I have just written like one paper,
Mhm.
which isn't even that great. But yeah, I think, we can ask.
If there is anyone in the audience who can maybe give a piece of their mind on this, be very helpful.
We can't unmute. I think you'll have to give permission.
I have given complete permission, so they can.
Hello.
Yeah,
Oh.
we can hear you.
Actually, the point just now which you have told, I completely agree to it, because like there are many constraints, and for which like we lag behind, like we can't go behind the very idea that we will do research, we will publish at a particular time. But there are constant pressure from the guide, I would say, that we have to like publish so and so number within this time frame, and there are many other things which I think is not like the scenario is completely different in abroad. So in IITs I have faced this, I have faced the like the same situation. So yeah, the things are very different here. And one more things, like here we have to qualify a particular exam, after that only we can move forward for the like research kind of thing. So the competitive pressure is always there. So I have seen many people like they leave all these things and go behind jobs, because the competition is so much, and after that we can like move forward the actual research. So I think this is one of the biggest challenges we face in the research field, which is not so in like abroad. Here we have to study all the subjects equally for the entrance thing. Like I am fully interested in biophysics, but I have to study each and every other perspectives of physics, starting from classical to quantum to everything, each and everything. So somewhere we lost the interest. So yeah, you were correct about that.
So maintaining the interest would be the right way to go, or do you think there could be a change that could be applicable from the basic part of it, from the fundamental part of it? Because it seems like this is going to stay for some time. This seems like the research community is going to face for some time, that they're going to feel the pressure constantly from the guide, and not just from the guide, from the university, from different institutions, to publish it as fast as possible. Agreed, speed is important, but the quality of research cannot be compromised for the speed of it.
Yeah, definitely. I think it's a problem I face as well. I wanted to publish my paper before I could apply to college, so that it could be good for my application, but it ended up just being a mess. My paper was not that great. I had to modify it a lot. So yeah, I mean, the key thing is that it probably takes a lot of experience to get things done in a short amount of time. Because if you're like a really good mathematician, physicist, or whatever, and you have a lot of experience, then you can write papers really quickly. Like usually the pace of writing papers in like STEM subjects, it can vary, but in physics at least it can be like 1 month. In 1 month or 2 months you can publish a paper. um, I've seen many scientists doing that in India, abroad, everywhere.
Mhm.
In universities, obviously, like we don't have a lot of experience, right, to write papers. This was my first paper, and it's going to take at least like 15 other papers, I think, to get acquainted with the fact that how to balance between time and this. I think it's just a self learning experience in the end. I don't think there's a solution to this if
Mhm.
the education system doesn't change. If there are deadlines, then I don't think there's a solution, right? You can't do anything about it.
Yeah, I mean, it also depends on who funds who and who funds whom, and that kind of affects it as well. That's I had a different question. Maybe audience might have something else in their mind, which if they would prefer to ask, that's also fine. It's a free running discussion. So feel free to unmute yourself and have a discussion round. That's also good. But in the meantime, what do you think about Neuralink? What do you think about the concept of Neuralink as a thing? It's not just physics sort of thing. It's a combination of it's a biophysics plus something else. Maybe even a
It's
bit of
a
computational
Elon Musk
superiority.
company, right?
Yeah,
Which
yeah, yeah.
I heard of it. I actually had an idea. Um, I was strolling in like a park. I still remember. I was strolling in a park. I saw these trees, and I was like, "This is so pretty." And back then, I was interested in a thing called graphic design. So I was interested in like Photoshop, and after I used to do a lot of video editing as well when I was a kid, and I had a lot of fun doing that. But it was really difficult. It was difficult to create like a pretty photograph in computers. It's actually easier to draw on the paper than to do it on computers. Like editing stuff is difficult. So I thought nature is so pretty, and we humans have seen nature, so we can imagine that. Why can't there exist something that harnesses your brain waves and creates the image that you're thinking about? And then I researched more and more, found that Neuralink can actually do something like that. I don't know if it, like, obviously it can't do anything like that, but that was my original motivation to understand like what Neuralink is.
Understood. It's a good project from that perspective. Since I saw that on your website, on the Wolfram Physics website, you are also interested into machine learning. You are interested into artificial intelligence as well. Do you think it will be the next step in the evolution of how we think or how we perceive physics, for example?
I cannot say. I don't know much about machine learning. I like know like the basic math of it, but artificial intelligence is like much broader in a sense. It's
It
not
is,
just
yeah.
machine learning. So machine learning is just a very small like mathematical part of it. Artificial intelligence is like it's like a whole different thing.
Yeah.
So I think I can't say anything about that. If anyone else has a better background in computer science, like Abhinav, you've done so much stuff with like space, debris collisions, and all that. Why don't you tell us about like how this might work?
This has been where, I mean, yeah, I have been involved with the spacecraft dynamics part of it for quite a while now, since my master's. Yeah, AI, as you said very clearly, that it's more than machine learning. Machine learning is basically Excel, which has doped itself, sort of.
Yes.
Yeah,
Yeah.
yeah, and AI would be more like applying that knowledge and applying your world knowledge from outside, assimilating the world knowledge and putting it into the action. That's actual human brain stuff, and that's what they're trying to apply with AI. Right now, I feel like AI has been in a very small, it's like a baby right now. It is growing. It is like a baby. It needs good food, good scientists, good research, sort of. It requires that field, but my field has been very limited to space related. And coincidentally in TOS, two of the people that I'm working with, they also studied with me in masters, and one of them was using AI, was using machine learning for his project. So it's it's quite an open field. Many people are using it, but it has got.
Can you tell us more about your project now that we can switch who is interviewing whom? Can you
Fair
tell a
point,
bit?
fair point. Yeah, so my project is more on collecting data and using artificial intelligence, broadly speaking, on spacecraft data to see if there could be potential collisions in space. So if there in the orbit there are so many junk that is flying around and potentially could make us like jailed within Earth. If you're planning to go to Mars, then good luck crossing that field. It's a tough situation. So my work currently compasses of understanding the planetary physics, understanding the space science, to the point where I can use AI to predict when next collision can happen. So inherently avoiding that collision from happening. So you can still have a chance to go to Mars with Elon Musk, I guess. That's the gist of the work that I do right now. Yeah.
What kind of data do you collect?
The data is from different space agencies. So the data would be more like a text-based thing. So you would be collecting all the mathematical, like numbers, like real numbers. You'd be getting lots of real numbers to play with, and the positions of the satellite, basically.
Okay. The position of the satellite, and this is basically a bunch of coordinates.
Bunch of coordinates, yes, bunch of coordinates, and then you predict with algorithm if that bunch of coordinates will be colliding with some other bunch of coordinates. Then
do you use a n-body simulation, or like that isn't really relevant here because they're very small, right? The chunks.
they're very small. You can even do it with a 3-body, circular restricted 3-body. That's also fine.
Yeah.
Not a problem on that front. But this is the gist of my work, and it's still going on. So anything considered space it's like keep it within the wraps. Don't say it out loud.
Right. Interesting. Okay, so can you go into the bit of technical stuff of your project? I mean, why do you want to, like you told me in the meeting before, that you need to study the geographical properties of the Earth and the atmosphere and the elevation of different surfaces? Like, why? Like,
think about it. Earth is not exactly a sphere, so the spherical community doesn't have a say over the flat Earth in that sense. It is kind of it's an oddball. It's a geoid, you can call it. Technically, yes, it's an oddball. So your gravity gets affected at every point. If you have, say, mountain or ocean or something happening, say even an earthquake can affect your gravity field in certain form or shape, depending on how deeply you want to look into it. So it is important to understand how the Earth affects your satellites in the orbit, like you suggested, like you said a long time back about the geodesics, that it's satellites think they're going in the straight line, but they are
but you don't need to but you don't need to compute geodesics, because if you start using general relativity in this project, you're going to get doomed. It's like you have to solve a bunch of 4-second order coupled differential equations, and then it's a mess. But anyways, Newtonian mechanics is, but I don't understand one thing. Why do you need to understand the fluctuation in the gravitational field when you're only dealing with objects that are very small, like debris? So why do those variations
matter? You're also dealing with megaton constellations, right? You're also dealing with so many different constellations. So let's just do a thought experiment here. Say you have you have a satellite that is going around Earth at 8 kilometers per second. So that's 8 kilometers. Imagine that. You're going at a high velocity, and now you have like thousands of them. And courtesy of Starlink, you're going to have 60,000 of them in the future.
But when is that releasing the satellites?
I am not sure. Right now it's about what, 4,000, 5,000? I'm not sure yet. It's a very chaotic system, to be honest. The way the satellite is dispensed into the orbit, it's a very chaotic system.
Okay.
And I'm very surprised that there has been no collision so far. But that's how chaos theory works. You have one sweet spot, you play around with that. Yeah. So yeah, you have bunch of them going around. Say 1 year down the line, you would not even 1 year down the line, give it about 10 days, 15 days down the line, you would have massive difference in the way the gravity affects the orbit.
Okay.
So if you don't know how the gravity is affecting the satellite, then you cannot predict what's going to happen to that. So it is very important to know whether the satellite, if there is suddenly, if you find out that there has been an earthquake causing all Himalayas to go down completely. Hypothetical, but if that happened, your gravity would be affected significantly as well, because Himalayas form a considerable chunk as a mass, so it affects.
So if a mass protrudes out of the surface, then Newtonian gravity tells us that the force should be the same because the mass is the same. But why does that vary? Like, why does the gravitational field change? I mean, general relativity says that it will change, but why? Like, can you give me a basic explanation of why it should change?
I think in this case, Revant, who is the techie behind this event, he has done practical work on gravitational field and altimetry and related to that. And he's one of my classmates from masters as well.
Interesting.
Yeah, he will have a higher say on this actually. I'm just
Right.
using the data.
Hey.
So, Revant, your video is not there.
You can't.
Oh,
I
yeah.
can see it now myself.
I can see
Okay,
it.
never mind. So I'm not exactly sure if I can answer the question. I mean, this last that you had, but let me try to explain like what exactly Abhinav is trying to say. So basically, Abhinav deals with like at the spacecraft level what's happening, or basically like basically monitoring and predicting the projectiles of the debris or the satellites. But how the equations of motions are governed there are like based on the spherical harmonics. Like basically your gravity. It's been quite a while since I studied this in depth. So,
Right.
so if you have any further technical questions, I would ask you to hold off until like I can probably like, or maybe just ask and like I'll get back to you later.
Okay.
So basically, depending on so we have the spherical harmonics, which basically show us like what is the resolution with which we can predict where the gravitational force, like what is the magnitude of the gravitational force. And at the first order, of course, we consider it to be just a sphere. And in the second order, the elongation and basically the spheroid nature of Earth comes. The deflation, the difference deflations at the poles, like neither the poles at the north and south poles, they are not deflated to the same rate. Then when you consider third, fourth, fifth orders, oceans versus like lithosphere comes into picture, basically the continents, because the mass distribution of the lithosphere or basically the like continental mass does affect like where there is acceleration of the satellite, because there's more mass versus less. And then of course mountain chains in the next order, and which is crazy because like these can be so easily observed using satellites, like, and they are being observed. And if you go even one degree more, you can easily also find like trends in variations over time if you have satellites continuously monitoring the like gravity measurements
So you're using
over a long
satellites.
period of time.
So you're using satellites to prevent satellite collisions. Interesting.
Yeah. So basically, what happens is all of these factors affect. Like even if there is like heavy monsoon in India, okay. So even that means that there is higher water content in the soil, and that increases the mass of the entire Indo-Gangetic plain, and that also affects the gravity field. Yeah.
Wait,
But of course, like
how does the mass of the Earth change?
Because because of monsoons now there is rain, and during non-monsoon periods all that rainwater is sucked out for agricultural use, and it's like and there is runoff or evaporation.
Yeah, but the total
And
mass
because
is
of that, there
conserved,
is
right?
observable. No, now it's elsewhere. Like satellites are not attracted to the Earth. Like you're considering Earth as a point mass, but that's not the case.
Yeah.
Yeah, yeah,
Yeah,
okay.
that's what I was about to
Like
say. On the whole, yeah.
physicist.
Yes, Earth mass is
Such a
conserved,
physicist.
So you're
Earth
saying
goes.
that
Yeah.
so you're saying that if water is in the form of like clouds, then the gravitational field will be less. Are you saying that? And like if the water is in the
No,
ground,
I'm saying that like water being on the ground provides a stable, measurable difference as opposed to some other time period. Because the time scales at which we are able to measure this is its order of a few months. That constitutes
oh,
one picture of the entire globe,
okay.
what the gravity fields are. Then in the
Uh,
next month, we get a new picture. So clouds
and-
are not resolvable at these degrees and these temporal scales, but these masses are, and definitely like Himalayas and these pose significant difference in the like where there is acceleration. So now what Abhinav does is take this spherical harmonics equations and uses them to very carefully and very accurately project where these debris are going to go. Because for major satellites that are really heavy, these things are important because especially for some of the satellites in geosynchronous orbit, which is where most of the geosynchronous orbit is where like a satellite is directly over one
yeah,
part of the Earth constantly.
24 hours
So at
period.
that, yeah, exactly. So at that altitude, the rotation of the Earth and the rotation of the satellite matches. And but that is a very particular narrow area, and there are like all the satellites have to compete for space, and there is a for no other space launches is there like any international regulatory committee, but for this particular thing there is, because there is such intense competition and need. So IAU basically allocates a very narrow space in the sky for each country, and like everybody has to apply. So so basically like there, if a collision happens there, all our communication is going to go down. So having like as good a prediction requires as a very good understanding of like the factors that affect uh, the all the forces that are acting on it. So now this is the gravity part of it. Then of course Abhinav deals with a lot more atmospheric. We think like atmosphere is still a continuum, like there are still ions. So all of these impact the velocity, especially when you consider that these things are going at relativistic speeds. You would definitely need like knowledge of any of the tiniest forces is going to impact the projectile in the long.
And
So yeah,
even
that's
in geosynchronous, there is a problem that the satellites don't stay in one spot as the theory suggests. It moves back and forth. There is a drift that happens. So if you have, say, a couple of satellites that are close enough, they could basically collide with each other. And that
Okay.
is not something that you would want.
So basically use a n-body simulation, right? Or do you actually consider the object as a whole object? But that how does that calculation even work?
Perhaps you could maybe let me know what you mean by n-body simulation in this specific case. Do you mean the?
I think talking about is like, are you considering the force of attraction in the satellites? In that case, the n-body, right? Is that what
Yeah,
you mean, Utkarsh?
yeah.
But that's not how you do it, right? You do have a more simple model. You consider each particle to be
Your voice is
independently behaving.
cracking. I can't hear
Yeah,
you.
I'm not able to hear you. Your voice is breaking up.
So I just meant, are you able to hear me now?
Mhm.
Mhm.
Uh,
Oh, we have.
so basically, I just was clarifying that what Abhinav meant wasn't that. Like you probably have a simpler model where each body acts independently, right? It's
Yeah.
or do you consider force of attraction between their bodies.
Yeah, I mean, you have n bodies, you treat them as point particles, and there's a force between each body, the gravitational force, and then you just simulate the parts of those things.
I think on a macro scale, your n-body simulations will work
Yeah,
effectively. Like, for example, if you want to consider, say, different planets, putting a satellite between different planets, yeah, n-body simulations would work fantastic there. It's complicated. Your system might blow up while doing that, but still, it can be done. But when you're considering space debris or something of that sort, your third body, which is your satellite, is almost negligible when you're considering the pull between the moon and the sun, and then you have Jupiter's pull as well. So you have different resonances that can happen. So you need to consider those things. So I wouldn't exactly say it's a pure n-body problem. It's a version of it. Like I said, like circular restricted 3-body problem would be more suitable for the kind of problems that we are trying to solve.
Okay, so out of all the factors you've told me, like this, the shape of the earth, the weather, the land masses, the etc. What is the factor that affects the most, like the orbits of the satellites and debris?
Earth's shape. It's the
Okay.
major contributor.
Mhm.
Then comes, depending on your orbit height, what matters is your aerodynamic drag that happens if you're like at 400, 500 kilometers. You would see that, as an example, one can definitely check this out on YouTube or even Google for that matter. ISS, International Space Station, has to constantly raise its orbit after some time. It has to, otherwise it will spiral down and fall completely.
Oh yeah.
The reason behind it is drag in the atmosphere. Simple. At 400 kilometers, you have considerable drag. At 800, somewhat.
What height is ISS orbit in?
I think 470 something, if I'm not wrong.
Oh, so it's completely like not outside the
It's low Earth orbit. It's in low Earth orbit, yes.
Mhm.
So yeah, it has to constantly raise its orbit every time to make sure that it doesn't fall back to Earth. So that's another factor going in the order of what can affect the most. Yeah, first thing is your that oblate spheroid. That's what they call in this thing for Earth, because it's fat in the middle, flatten at the pole.
Yeah.
that
So the gravity
affects,
is more in the equator side, right?
you have a stronger pull, yes.
Yes.
And you also get you have solar radiation pressure, which is
Oh my God.
that's another thing. Understanding the solar cycle is very important. It's every 11 years you have a solar maximum, you have a higher flux of solar particles hitting the satellite. It could pretty much deorbit a satellite if it hits all at once. That's also a possibility. Not completely, maybe it could deorbit it to a lower level and then it will fall down by itself. These are certain impacts that happen. Also, your tides on the planet can affect it. Your ocean tide, those
But
also
tides are
affect
due to like the tides are due to the moon's pull on the Earth.
moon and
Yeah.
And they also have an effect on the satellites themselves.
Oh, so it's like a loop, right? Interesting.
Yeah, and
This
and,
is
and Jupiter
complicated.
and Saturn have an impact. Sun and Moon have the most tidal impact, and then so does Jupiter and Saturn.
Yeah. Wow. Mars doesn't have any impact.
But those are like
those are massive planets. Mars is smaller than Earth in that sense.
Yeah, but it's much closer to like.
Theoretically, yes, it has impact. Kanika has a question for Utkarsh. What kind of research work did you do at CERN?
Well, I didn't do any
and I
research.
would encourage Konika.
Please join.
Sorry, I just wanted to just join Konika. Like I think we might be able to learn a few things.
Now,
from
this
your
is a
research
complete
together.
free running session. The podcast theoretically between Utkarsh and myself was done long while back. So feel free to jump in. It's a networking session. Feel free to jump in.
Yeah. Go ahead, Utkarsh.
Right. For some reason, my internet just What do you say? The question, what research work did I do at CERN?
Yeah.
Yeah.
So I did not do any research work at CERN because, well, I just visited there when I was in 8th grade and I didn't even know what the standard model of particle physics is. So I just went there, I got fascinated, bought a t-shirt, didn't buy a t-shirt actually, metaphorically bought a t-shirt in my brain, came back and just got, interested in physics. So no, I did not do any like research work at CERN. It was just like a 1 day guided tour of the interesting thing. The mascot of CERN is an Indian goddess. Who knew? I researched that before going there, and then they showed it to me. So yeah.
Wow. Okay, that's something new. I just knew that there is a statue in front of CERN of Nataraja, that Tandav pose. So
I don't know actually. I forgot, but yeah.
It was an Indian gift. I think India gifted to them a while back, a long time back actually.
I don't know, but the thing is, in CERN, okay, so the CERN is like this wooden dome in the center of a grass field. That's what CERN is. And once you go over there, inside the wooden dome, there's the first thing tourists usually go to is this place where you see it's all dark and there are like red lights, strobe lights, like really cool stuff. It's not exactly a disco, but the thing is, if you go inside, they have these glass boxes, and inside those glass boxes are like facts of physics, like this is equal to this, or this is a fact of physics. And that was itself so like it's so neat. I went there, and then there was these chairs with headphones on. So I sat in a chair, reclined, and there were these headphones telling me about like the mysteries of the universe and all that. And then from there in CERN, we went to where did we go to? We went to the actual kind of working area of CERN, and we were outside, so we were seeing the workplace, and there were like these large computers and all that. Iron Man's workshop, real life. And then in and then our guide was showing us on TV. So CERN has like a bunch of TVs here and there which show the results of experiments. And on one of those screens, he was showing us the fluctuation in the graph, which corresponded to the Higgs boson. So and for people who do not know what the Higgs boson is, the Higgs boson is a particle which was discovered in 2012 by CERN. And it's the particle that actually gives other particles their mass.
Boson, something. Higgs boson.
Higgs boson, yeah.
Yeah.
It's called the God particle. I don't know much about it, but yeah, it's part of something known as quantum field theory. So actually, should I just show the demo which I had on the Wolfram?
Sure, yeah.
Yeah, go ahead.
Let me just so the thing is, I originally planned to do some live coding, but I'm not that great at coding now. So I'm just going to show you some interesting things. Let me just set this up.
Maybe in the future session about coding, maybe you can show something.
That'd be done when I'm good at coding, actually. So right now, okay. So let me share my screen. 1 second. Let me just make a few adjustments here and there. Can you all check? Can you all see my screen?
Yeah.
All right. So this is going to be fun. If my computer doesn't hang a lot, but so this is one of the things that I wanted to show you. This is an interesting image. Right. This is known as a hypergraph. So I'm going to tell you what hypergraphs are, but first, a hypergraph is like, it's this, okay? It's this, and according to the Wolfram Physics Project, this represents space itself. So you and me and all the particles are actually parts of the hypergraph. They are sub-hypergraphs. So they're a collection of nodes and edges. So for example, this is also a hypergraph.
Is this developed in Mathematica?
Yes.
Oh, okay.
This is Mathematica. So This is a hypergraph, and the red edges you see over here, that's called a sub-hypergraph. In fact, in this case is just a graph, not a hypergraph, but these sub-hypergraphs represent things in the universe, and this underlying structure itself is space. And so general relativity is about how space-time actually is curved and all that stuff. And I'm gonna give a very basic preview on this thing. So let me just do this. So it all starts with a thing, like an idea called computational thinking, which is probably the core of self-learning. So computational thinking is when you have nothing to do, and you just come and you just sit on a computer and do experiments, not actual experiments, but theoretical experiments on the computer. And those experiments, without any guidance from any textbook, is known as computational thinking in its rough sense. So let me give you an example. So this is where the power of computational thinking comes in. This language called Mathematica was developed to actually emphasize the power of computational thinking, so that students or people can, without limited amount of coding, they can produce the maximum output. So that most of the work is done by the computer. So that's the goal of Mathematica, to make it as transparent as possible. So let's see some interesting things. Let's see. So let's say I want to plot a graph of x squared with respect to x, obviously. And let's say the domain is this. Oops, sorry. Let's see. So this is a graph of x squared. And then, so you can probably like label.
Is it a separate language or something? Mathematica has a different language than standard coding like Python, MATLAB, or something like that.
Yeah, so this is a functional programming language. So a functional programming language means that everything is done using functions. So, like if you want to do something, there is a function for that. So for example, this program has its roots in something known as Lisp. Lisp is the world's second, I think, the second oldest computing language, and Lisp is also a functional programming language. So Lisp is also a functional programming language, and the thing is that a functional programming language is kind of like it uses functions to do stuff. So for example, if you want to add two numbers in Mathematica, you can just say 2 plus 3. It will give you the answer. But in Lisp, what happens is that there's a function for that. So the function is always written in this form. You have plus, and then you have 2 and 3. This will give you 5 in Lisp. This is the syntax for Lisp. Mathematica is like a much more evolved version, in a sense that it allows you to do more things. First, and second is it is a symbolic computation language. So in Lisp, if you do like plus, okay, let's see. If you do in Lisp, if you do plus xy, it would show an error, because x and y are just two things that have no like numerical value. But in Mathematica, if you do x and y, it will just give you x plus y. And if you say that x is equal to 5 and you run this, it will give you 5 plus y. So with this language, you can do like so much stuff. I mean, with this language, you actually do what is like, you do computational thinking. So this is a graph of x squared with respect to like x and so on. And then you can do all sorts of stuff with this. Now, the interesting thing is this. How can Mathematica be used to enhance student curiosity? So this is where it all comes in. We all know कि class में हमें सिखाते हैं कि x square को ऐसे plot करते हैं. Oh wait, I labeled the axis wrong. Sorry. Right. So in class we learn that we learn how to plot graphs. We learn how to do all sorts of stuff. But the thing is, we are limited by notebooks. This is the interesting thing. A notebook is just a piece of paper, a collection of pieces of papers, and when you draw something, you can only draw a two-dimensional figure. Mathematica is also a notebook. This is a Mathematica notebook. But the thing is, this allows production of 3D things as well. So there's a thing called plot 3D, unlike the physical notebook. And you can, let's say that x squared plus, let's say, y squared. I have already defined x squared. So let me just clear this. So you have to plot x square plus y square, and no one in like a no one knows in the classroom what would this look like, because we can't possibly draw a 3D graph. It is very difficult. We can, but not an accurate version. So let's see, we can plot this graph as well. Minus 5 5, and we'll get some interesting shape. This is all about you can do like literally everything, anything you want over here. You can just do like 8x square. Let's just do some fancy thing. I don't even know what I'm doing. Why, I don't know, tan, let's throw some arctans in there.
I think this is the way to learn coding, to be honest. You don't know what you're doing, just keep doing it.
Yeah, but Mathematica allows you to learn math and physics using that way, because the outputs that are like you are producing a math related output, and the thing is, the coding is really simple. Mathematica doesn't take a lot much time to learn. Like, that's the point of computational thinking. You can learn other subjects by just exploring. It's like the whole thing is an experiment. So there are other things as well. So let's say I want to plot a sphere, and plotting it with x square. Okay, so how do you plot a sphere? You can either, equation of a sphere is x square plus y square plus z square is equal to r square, but it's kind of difficult to plot it because, I mean, you can't just take every point which satisfies this equation. So there's something known as a parametric plot, and you can do that. So you have like 2 parameters, let's say. By the way, how much time do we have for this?
Let's see after this, because by 3:30, 3:30 I have another meeting to attend, so that's all right.
Okay.
My time 3:30 is yours, would be 3:30, so 7, I guess.
I guess I have to kind of do this a bit quickly. Oh, wait, this is not. This is and we know that like we know what spherical polar coordinates are. So I can I forgot the equation, but I'm just gonna give it a trial to see whether it works or not. Let's see. I think it's gonna be wrong. I don't remember the exact form, but let's I don't know. This is definitely correct. The last one is also correct. Let's see if we get a sphere. Yes, we do. So this is you can actually plot a sphere by just entering the parametric form, and like you can do like so many interesting things. Okay, now I'm going to tell you about the Wolfram physics project. Before that, let's actually look at what cellular automata are. So this is a screenshot I took just before the meeting from Stephen Wolfram's let's see, A New Kind of Science. And so this is a book which kind of replaces traditional mathematics with computation. Like, not exactly, but it's a different way of looking at the world. So the whole idea of the Wolfram physics project is based on the fact that simple rules can lead to complex behavior. It can lead to behavior that cannot be predicted. So, and what do I mean by behavior? So it can be any kind of system. So one thing is let's say the 3-body problem. The 3-body problem is a very famous problem in the sense that there are many solutions, but we just have to keep finding them. It appears non-deterministic in a sense that we can't determine what's going to happen, but Newton's laws are inherently deterministic. In this case, what happens is, this is also the laws by which this thing evolves is deterministic. We know the rule that we are going to apply, but the actual outcome is unpredictable, which is why I said that the rule of the universe is simple, but the evolution of the universe is complicated. So let me give you an example where this might show up. So a cellular automaton can be thought of as a bunch of cells, like a bunch of cells on a screen, which are either black or white. So every cell is either 1 or it is 0. If it is 1, it is black or white or whatever choice you make. And if it is 0, it is, the other color, one of black and white. So a cellular automaton is a rule. So it means that this is an example of this rule I'm talking about. If you have 3 black squares on the top, then on the next step, so this is, for example, step 2 over here. On the next step, you should get a black square on the center cell. If you have 2 black squares and a white square, the center cell should be black. So I'll just read this out. The cellular automaton consists of a line of cells, each colored either black or white. At every step, there is a definite rule. In this case, this is the rule. that determines the color of a given cell from the color of that cell and its immediate left and right neighbors on the step before. So if this is a cellular automaton, the step 1 is just a collection of cells. Then we apply the rule and produce step 2. Then we apply a rule and produce step 3. So let's look at rule 254, which is this rule over here.
Okay.
And we start with one black cell. This means that the other cells are white. Think of it as this: there's only one black cell and at the center. So in this case, there's a black cell over here and white cells like otherwise. So there's a white cell on the right and the white cell on the left. If we see this rule, what pattern matches this? This one, this cursor one. There's a white cell on the left, a black cell on the center and the right, and a white cell on the right. And if the rule is applied, that means on the next step, there should be a black cell below this. So what I mean is, if the step is number 1, so this means that there's a black cell over here, which is just beneath this cell. And then you apply this rule, and these are basically all the possible combinations you can get of the top row. And the rule is basically what should be the color of the center cell. And if you start evolving this, you can produce some good patterns. So let's say after
like discretizing it for some reason.
Yeah, exactly.
It's like discretizing it.
Exactly. That's why spacetime is discrete. I'm going to come to that. So let's say after 15 steps. So it's kind of easy to predict what this is going to look like after, let's say, 1,000,000 steps. It's just going to be the staircase, right? There's another rule called rule 90, which is also predictable, but it produces something known as a Sierpinski mesh, which is another mathematical shape. But this is the rule. So the rule is different. It's called rule 90. And so over here, we saw that all of these were black, which is why this whole figure is black. But some of these are white. So we get this figure. So let's say after 1 step, we get this. After 2 steps, we get this. After 3 steps, we get this. After 50 steps, oh shit. I did 350 steps, which
will take some time, I guess.
Yeah, I think I'll just abort the evaluation. Oh wait, luckily it didn't, because oops, what's happening? Something wrong is happening. I don't know what's happening. Let me just disable my other keyboard if that's the problem. Nope. I don't know what's happening.
I think it's kind of there's some error, I guess.
I think it's fine now. It's fine now. Yeah. Anyways,
was it computing?
I don't know what's happening. Let me just rewrite this code actually. Array plot. नहीं तो कुछ अजीब सा हो जाएगा.
It's like there's a stick man that came alive.
Yeah,
on your screen.
Usually never, like something like this never happens. Well, anyways,
this is very common in coding, ma'am. This is very common in coding. This is kind of
I mean,
depend on this.
It crashes a lot in my computer. I think one day I might kill my computer with these computations. Anyways, so this is what happens after 100 steps. This is very intricate pattern, and this is known as a fractal. That means if you zoom in, the pattern is going to repeat itself. So this is a very like standard pattern which can be predicted. So after, let's say, 1,000 steps, we can predict what the figure will look like. Now comes rule 30, the most famous cellular automaton. Let's say this is the deceptively simple rule. Now let's see what's going to happen here. Something really interesting is going to happen. If I can figure out how to code this thing. Yeah, okay, let me just rule 30. And let's say after 0 steps, there's just one black square and the other squares are white. So there's a black square in the center and 2 white squares. So the ye wala black hona chahiye, and then we can just apply these rules. The computer does that for us. After 1 step, simple. 2 steps, okay, interesting. 3 steps, 4 steps, 5 steps. Like, okay, so it's too early now to see a pattern. So I think we need more kind of steps. So let's see. Let's do 10 steps. Okay. 20 steps. Okay, so this is kind of neat. This side is at least predictable. What's going to happen? This side is a bit funky. Let's see. Maybe a pattern will emerge. Okay. 50 steps. So we can see that the left side of the cellular automaton is kind of uniform, but I don't know what these are, these funnel shaped things. Okay, let me see, like let's say 70 or something. Okay, 100. Okay, okay, we start to see some interesting stuff. Like still no pattern, but okay, we can't see anything. We can't see anything. And see, so the left part of the cellular automaton is kind of uniform. But this uneven distribution of sprinkling has no pattern. It has been statistically tested that this has no pattern, and we cannot predict what the next row of cells would be. The only way to do so is to just evolve the system.
There is a reason why.
The reason is computational irreducibility. That's the reason. So
Okay.
yeah, it is explained, like I can't explain it now, but it's related to something known as the principle of computational equivalence. So the more, okay, so this might not seem as mind-blowing, but the reason why it's mind-blowing is because we had a rule originally, and that rule should produce a pattern.
Yeah.
But how is it producing something non-deterministic? I mean, not exactly non-deterministic. We know how to apply the rule, right? We know how the thing is going to evolve, but we can't predict. Like we know what to do, but we don't know what the output is going to be. And there are other rules as well. There's something known as the rule 1110 or something. Wait, I think it was rule 1110, right? Which is even more unpredictable. That's like the most unpredictable rule, I think. I think so. I don't know. I think it was some other rule, but I don't know. Yeah, exactly. This rule is also not predictable. You can see this intricate pattern that is forming over here. If I zoom in, you can see that there is no uniformity, and you can go on and on and on, and you'll never reach a conclusion. There's actually a funny story about this. Stephen Wolfram discovered this in, like, when he was in Caltech. He was doing his PhD when he was 20 years old. So he was in Caltech, and what he did was he discovered this weird thing. He actually printed this thing out on a large chart paper to see whether there was some pattern, so that he used a large ruler to actually see whether there were patterns, and there were no patterns, like in the case of rule 30 as well. So guess what I'm trying to say is, if you have an initial state, which in our case was just this black box over here, and if we evolve it by some rule, it is going to produce either deterministic or non-deterministic behavior. But it's really like some rules exist that completely like just blow up. There's no way to predict what's going to happen. And this is a computation which is known as a sophisticated computation. So it is as sophisticated as something that is unpredictable. And Stephen Wolfram's great principle of computational equivalence says that if there is a computation which has an initial state and a rule, and we know how to apply that rule, there is a set of rules that produce unpredictable behavior, and all of them are basically the same. He said that those rules are equivalent because they basically are very sophisticated. So even if we use just like a bunch of cells over here, later I show that the same thing is happening with the graph. So we start with an initial graph and we evolve that graph. So the graph is actually much different than the cells and more complicated. But the thing is, the rules that are basically the same, right? And they both are sophisticated computations. So all of this works on the principle of computational irreducibility. And the statement of the Wolfram Physics Project says that we can evolve a universe by a simple rule, but it will produce complex behavior, because the universe we live in is unfortunately very complex. It is simple because we observe patterns, but it gets complex when those patterns break down. So general relativity is also a pattern, not exactly like a pattern, but it breaks down in like black hole singularities. It's something known as called geodesic incompleteness. And general relativity breaks down there. It basically says that there is no space and time at the center of a black hole. There is literally no space and time. It ends there. And that's why the Big Bang theory is like proposed, because Stephen Hawking said that the universe should start from a singularity, because at the singularity, space and time doesn't exist. So the Big Bang theory should be the point where space and time starts to exist. So that's why if you've seen the Theory of Everything movie, Stephen Hawking says that what if the universe started from black hole? Because a black hole, at the center of a black hole, the space and time cease to exist. Anyway, I'm going to skip over this for now, but the key thing about the
Do
Wolfram
share
project,
this, but do share this with us, because we can put this in our in the resource material that we will be providing via email. So this is a fantastic workbook that you have. So you
I don't think this is a good workbook because it's just like very rough. What we can put in the like the resources is a bunch of links that link to the documentation of this. Like,
yeah, but people would love to try this out as well. So
yeah, but they won't have
learning through
Mathematica, right?
experimentation, you know.
I think they need to download Mathematica first. So
Okay.
yeah, I think we
We
can
will work out on that. Maybe
Yeah.
I'll have a separate session with you to just figure out how to create this as a step-by-step procedure, and then we'll post it with the email. That would be helpful, I suppose.
Yeah, sure. Okay, so I think we're running out of time, but let me just quickly go through this. So the thing in the Wolfram physics project is that current theories of physics assume that space and time are continuous because it's easy to do mathematics with it. So it's easy to do calculus is based on the notion of continuous, right? We can only differentiate something at a point if it's like continuous, because differentiability implies continuity. But the thing is, the thing is, those theories are approximations to something that is more underlying, which is more complex. So general relativity is an approximation. It assumes that space and time is a continuous manifold. Manifold is a technical term for a curved surface. Like you can think of it as being a curved surface, but whatever. So that is the claim of the Wolfram physics project, that the current physical theories we have are called pockets of reducibility. So the whole theory is computationally irreducible, but there are pockets in which humans can see stuff that have patterns. But those pockets of reducibility are only valid in a certain area of the whole computational irreducible picture, which is why singularities exist. Like singularities are predicted by general relativity, even though they do not exist. So
maybe, maybe Utkarsh, I think we will have to do another session on this properly, just on the concept. Like I said initially during the podcast, that we need to do a session on computational irreducibility, because I'm not completely aware of it right now, but I'll surely be happy to learn this, to be honest. And I think even the viewers would love to know more about this. What do you think? Would you be with another session going forward?
Sure. Okay, but before, just one last thing.
Yeah, sure.
I would always like to show some pretty pictures that you can like produce. So this is the universe after 5 steps. Okay, this is the universe after 100 steps. Okay, and this is the universe after 500 steps. I think it's going to take a while. Okay, yeah. So and the claim of the Wolfram physics project is that after many steps, this universe is going to look like a continuous surface, which is what is said by general relativity, that the universe is like continuous because we perceive it to be continuous. We want our theories to work in a continuous sense. So this underlying discrete world approximates a continuous thing. And that's why we say that in the Wolfram physics project, current theories are in the continuum limit of the discrete theories. And so there are these other interesting pictures you can form. These are known as multi-way systems. This is related to quantum physics. And then there are like these other things that you can produce. Let's see this. Let me just 1 second. I don't know how much slow my computer is, but I think, yeah, the goal is like, yeah, you can, the goal is use Mathematica because you can do computational thinking with it, and you can just learn by experimentation. That's the theme of Mathematica, learning by experimenting. So I think I'll stop sharing. And
that's a good presentation, Utkarsh, and definitely I would love to do another session on this one, just to, just for my own personal sake, but I believe even people who are still there on the call would love to know, because they have stuck around until now. So thank you. And you will be able to, we will send you all the details when we are doing the another session on this with Utkarsh, and maybe even bring out another person from Wolfram.
Yeah, I can ask them if they'd like to come. Definitely.
bring in more people on that direction. Let's do a separate session on this in the future. So thank you all for joining today's session, and please don't forget that the session is available on our YouTube channel. So please like, comment, subscribe, share, and all the good stuff. Yeah, just do all the good stuff and let us know how the session has been. And don't miss it. Tomorrow we have the final wrap-up session with HC Verma Sarji. So do join, and it's going to be from a educator perspective, not just from a physics perspective, and maybe we might get some good idea for a future possible white paper on this. So looking forward to that. And our
Mentorship
channel
thing?
is DOS, the Out of Syllabus Society. Do have
What
a
about
look.
the mentorship thing, right? There was a
Mentorship, definitely. So we will look into this, and there are students who are actually interested to know more about that, the mentorship direction. So we will host this information on our via email as well as on the YouTube. So we'll keep you in loop on that, Utkarsh, definitely.
sure.
So that's all from our side for today. Thank you. Good night, and see you tomorrow.
Thank you so much. Thank you
Yeah.
everyone for joining.
Thank you.
Bye-bye.